Reminder, record to the. All right, good.
So good man, yeah.
You've done your job today.
Sir.
All right, it's 8 o'clock. I've already been up for almost 2 hours.
Where are the donuts?
Oh yeah, well, they're actually the dog woke me up. So well, good morning. And I have no idea how many people are going to show up. And to be honest, it really doesn't matter because I'm here and all you guys are here. So that's a really good start. If you haven't modified your name by putting your call sign up there, because it's not just for me, it's actually for everybody else as well, that would be a really big help. So the first thing that we're going to do is say congratulations on getting your technician license. Some of you, I'm just curious, how many people here have had their technician license for more than 10 years? Because you've got a WB call. So Russ, not to put you on the spot, but when did you get your license?
I got myself unmuted here. The answer to that is I don't know. I think it might be in the early 80s, early 80s, but I haven't been able to find anything on the FCC or any other place that shows me when it was originally issued. It only shows the current license that runs out, I think, to 27.
Okay. Well, all right. Let's see. Anybody longer than, well, let's see. So you're in the 80s. Okay. You know, interestingly, in one of the last classes I did, we had somebody who signed up for the technician class license, the technician class that I did. she'd had a novice since 1986. And said, you know, my dad's a ham, my mom's a ham, my husband's a ham, I'm a ham, but I've never really done anything with it. And I'm getting ready to retire. Maybe it's time to start doing something with it. So over a period of a month and a half, she went from the novice, which you can still have, to an extra, and is now like really active and is as a volunteer examiner, a lead for VEing and things like that. So she's, as you were saying, Ramon, she found her niche, right? It's just that the niche had to wait for her to get there.
That's a beautiful thing within itself, because there's just so much, and some people, she may have fell in love with the actual testing side of it and the education side of it, and that's okay. That's beautiful, because it helps everyone else like us to be able to do what we want to do.
Yeah, exactly. So, all right. Well, the first thing, okay. So what we're going to start with is the math. And the reason we're going to do math is because this is the general class, and the general class relies on mathematics quite a bit. So there's some basic fundamentals that we're going to do, which on the technician license, I sort of cover, but not really in detail. But on the general class and above, it's really kind of necessary. So everybody, I also like to do a very interactive class. So feel free to unmute yourself and answer questions and ask questions and stuff like that. All right, everybody, what is this a crudely drawn thing? What is this thing?
Phase map.
Okay, well, I mean, but what is it really?
The unit circle?
It's really an ugly circle, exactly. Okay, so all right, so a circle has basically, we have two axes, coordinate axes. We have the x-axis and the y-axis. If we had the z-axis, it would be coming out of the page toward us. So we're not going to draw the z-axis in this case. So on this coordinate axis, by definition, we have this thing called basically the origin, which is in the center, and then we have our 0-degree line. How many degrees are there in a circle, everybody?
360.
360. Okay. All right. So we start at 0 degrees. And by definition, when we start measuring angle, we go in a counterclockwise fashion. So we start at 0 degrees. When we get up to the top, which is right here at the yellow dot, we are at 90 degrees. When we get to the green dot, which is all the way on the left, we are at 180 degrees. When we get to the blue dot down at the bottom, we're at 270 degrees. And we get back to that first line that we were on. We're at 360 degrees. Well, so what do we notice about that position right there? How many different names does it have?
Four?
Four.
It's got how many different angle names does it have?
Two.
It
So
is
360.
But in fact, what if we were to keep going and go around the circle again? And the next time we got around, we kept adding and we were at 720. And the next time around, we were at 1080. So in actuality, every one of these points on a circle, if you're talking about the angle, has an infinite number of different names. Because it can be like this can be start at 0, 360, 720, 1080, and so on and so forth. And that circle never stops spinning. We could keep adding and subtracting 360 from that point. So we could also say that it's negative 360 and negative 720 and so on and so forth. For the sake of argument, though, what we're going to do is just say that this is our 0 degree mark. It's kind of our reference point. We're going to call it 0 degrees. So now what we're going to do is take a look at this and we're going to say, okay, we're going to have this being our angle right there. And we're going to have this being our amplitude. All right. So what are the interesting points that we marked on that circle? There's 0 degrees. We have another mark at 90 degrees.
90, 180, and 270.
Exactly. So here's 180. And here's 270. And now we actually need to use that other name to finish the circle. We'll call it 360. So this is actually one complete cycle, 360 degrees. So now we're going to introduce something else. We're going to introduce a point on this circle. And we're going to call this distance equals 1. In other words, that point is traveling around on the circle a distance of 1 unit away from the middle of the circle. All right, so if I've defined that, does anybody know what this circle is called? It actually has a name now. This is called the unit circle. Right? This actually has a name. And the unit circle is made up of all the points that have a distance exactly 1 unit from the center. Okay, so now if I were to draw this point or this point or this point, those would all have a distance 1 unit away from the middle of the circle. Okay, so what this does now is this allows us to do a little bit of interesting math here. If I make this a right triangle, does everybody remember the Pythagorean theorem?
Yes.
Okay, so if I have an X and a Y and a Z, by the Pythagorean theorem, X squared plus Y squared equals Z squared. All right, now the distance is 1. So I know that Z is 1. So X squared plus Y squared equals 1. So now if I also can look at this unit circle and this triangle that I made right here, and I have an angle right here, which is the angle that the line has now rotated from that 0 line, I have 2 functions. I have an X component and a Y component. And it turns out that X is equal to the cosine of the angle whatever that angle is, and y is equal to the sine of the angle. So by trigonometry, the sine is equal to y divided by z. This is equal to x divided by z. Well, we know that z is equal to 1. So in this particular case, the cosine of theta is equal to x, and the sine of theta is just equal to y. Well, we can now plug these into here, and we find that cosine squared of theta plus sine squared theta equals 1. I'm not going to answer that. So basically what this now says is, hold on, I guess I do have to. Nope, my wife got it. Okay, so now what this really means is that we now have this x squared plus y squared equal 1, or cosine squared plus sine squared equal 1. So what this means for us is that because this is a right triangle, we can always figure out what that value is and what the x value is and what the y value is, just given the angle. So the interesting thing about this is that now we're going to erase that stuff because we now know that it's true. We're going to start plotting the positions. We're going to start plotting, for instance, in this case, we're going to look at how far removed from the x-axis.
The guy called and said he sent you a message, there's no link on Facebook, and he sent you, I don't know, he said he sent you a message through Facebook.
Okay.
You
Somebody's having trouble getting in. Okay, so let's see. So we basically are now looking at how far off of that X line we are at any given angle. So we know, interesting point, that if we're at 90 degrees, we've now gone straight up. We're 1 unit up. If we're at 270 degrees, we're 1 unit down. So that would be called -1. And at this point, and this point, and this point, we're right on the X line. And now we connect the dots. Does anyone recognize this thing?
Mhm.
What, it has a name. What's it called?
Waveform?
Sine wave. Okay. And now, interestingly, the reason that it's called a sine wave is because y is equal to sine of theta. Well, look at that. We have our y, and there's the term sine. So that's known as a sine wave. So now what we're going to do is look at another version of this and say what we're going to do is plot the distance away from the y-axis, so from the vertical axis as our circle spins around. Well, at 0, we're a distance of 1, and it's +1, because this is the positive and minus, and positive and negative. So it's going to start up here. As we come around here, we're on the y-axis, so we're here. Then we come over to here, and we're -1, and we come back to 0, and we come back to 1. So guess what we do when we connect the dots? Okay, so this is, what kind of wave do you think that would be called, everybody, considering that x is equal to the cosine of theta? That has a name. If the other one was a sine wave, what do you think the other one's called? Cosine wave.
Yeah.
That's right. Okay, now, the other thing that's important here is that to note is these look exactly the same, right? And what do we know about circles? If we start going around and around in a circle, what will happen if we keep going?
Let's come back to the same place.
It'll just repeat itself over and over and over. Well, okay, so really what we've done is we've just taken a snapshot of this picture in time. And if we were to take this cosine wave and move it 90 degrees, what would happen?
They would phase together.
They would be exactly in phase. That's right. They would be right on top of each other. So the first and very important thing that we're going to cover is not only that there are these waves, but now we have discussed, and this is going to be very important, this thing called phase. So these two waves have a phase difference of 90 degrees. So the maximum phase difference you can get, it would be 360 degrees, which would be 0, right? Because it's all laying on top of each other. You can describe phase as being positive shifted or negative shifted, but essentially the only thing, what's important to note about phase is that it causes one wave to be shifted in time or in angle from another one. So if I were to draw two waves that were completely out of phase, I could draw this. Something that's out of phase, I would start it here and I would do this. So really, these two waves are
Who said it was going to go that far south?
Hello? What? Oh. All right. So these two waves are now complete 180 degrees out of phase. Because if we were to look at the same exact spot, we would see that there is a difference of 180 degrees separating them. So let's say that we instead have two waves that look like this. There's one, and here's another one. All right, we might have a phase differential of, let's say, 3 degrees here. So one is leading or lagging the other one by a very, very small amount. So they're almost in phase. Two waves that are perfectly in phase will completely overlap. Now, interestingly, they might not be the same amplitude. They might not be the same amplitude, but they do have the same angle, in which case they're basically peaking and valleying at the exact same time in space. So very important concept. So, all right.
Does this
Any
account for
questions?
does this account for distortion on the frequency where they only want you to have about 3 megahertz difference? Or the allowable, side bands on either side?
No.
Okay.
No, what this does is this gives you something called multipath, because frequency and phase are very different things.
Okay.
Basically, I mean, if you think about it, there's two fundamental parts of any frequency. There's the frequency, which is defined by the period,
Wavelength.
right? So it's frequency, period, wavelength. But then there's also the phase. So now if I were to take a look at something that's a different frequency, right? They can interact with each other, but they're not consistently interacting with each other. Now, something that's a harmonic that would look, for instance, like this, where it still lines up, could do something.
Get an echo?
It could, yeah, it could actually peak and valley. The other thing is that if you were to have two waves that were off by a little bit, just a tiny bit in frequency, basically the differential would continue to grow, right? So these things would actually cause, if you added them together, a beat frequency. Do we have any, are there any musicians out there? Raise your hand if you played music. Do you know what it sounds like if you have, let's say you're tuning something and you are about or let's say 2 hertz away from tuning your guitar string properly. What do you hear?
Ding, 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 ding.
That's known as a beat frequency, and that's caused by a slight differential in 2 different frequencies adding together. Right? But normally we're not going to mess with that, but that is a way to figure out, you know, how far off you are. If I were to draw this on a different kind of chart, right? So where I instead, let's say I did a frequency transform and I have my frequency versus amplitude, I would actually see something here and something here. And these should not, you know, on an amplitude level, really interfere with each other all that much, right? The big concern is that if you have these, then if you end up with 2 things that are in phase, or sorry, 2 things that are on the same frequency, but out of phase, they'll actually cause cancellation. So let's say that you have this, that's a fundamental wave that's coming in from some source, and another signal that, because the path, let's say, to get from point A to point B, point A, and here's point B, there's the one path, but then there's another path that, because of atmospherics or physical objects or something, took slightly longer to get there. Well, if it's delayed in time, what does that mean about the phase?
Right, at the same time, they're not in phase, but the time.
Right,
the
and in
angle's the
fact,
same.
it would take longer and the phase would be delayed. Now, if the phase is delayed, you don't know unless you actually measure how far it is, how, you know, what the physical difference is in distance. It could be delayed. Whoops. It could be delayed 360 degrees, in which case it would be in phase. The amplitude might be different, but it would be in phase. What if it's delayed 180 degrees? I could still draw that wave, except now it's out of phase. And what you get at that point is this thing, the red is called constructive interference, and the green is called destructive interference.
One is boosting the signal, the other is degrading it.
That's right. This is evidenced by the fact that you can take your handheld radio. Let's say we go to the 2 meter band. What's the wavelength of the 2 meter band? Approximately
2 meters.
2 meters. Okay, which is how far in feet for those of us who speak imperial units?
6 feet.
6 feet. So it's about 6 feet. Okay, so let's say that you are talking to another station and you have a direct line of sight, which is some distance d. Now, you also have, unbeknownst to you, a pickup truck that is parked somewhere where the signal is now split, because, you know, the signal that's going from point A to point B goes all different directions, right? Only one signal ideally gets to you. The rest of them kind of don't. But let's say that you have this mysterious pickup truck, which is now right there and is bouncing a signal which you did not expect to be getting to where you're expecting it. You're getting a secondary signal that is traveling some distance d plus delta d, which is a change in distance. Well, okay, if both signals were going the exact same distance d, they would get there at the exact same time. But what do you know about the one that has to travel the extra distance?
You should only be getting a portion of the transmission occasionally, as it arrives at the same time.
It's always there.
Okay.
but it actually has to go that extra distance. How fast do radio waves travel?
Speed of light.
Speed of light.
Right.
Okay. So if you know how much extra distance it has to travel, could you figure out how much longer it would take to get there?
Yes.
You can. And you know what the amplitude is, or sorry, you know what the frequency is. You know what the wavelength is. It's about 6 feet. You know that this might take an extra, 10 nanoseconds or something like that. And you can figure out how much delayed that signal would be in getting there. You could actually plot that and find that your two signals, instead of being additive, are actually looking like this. It's a different amplitude, but they're out. Let's say it's 180 degrees out of phase. It's still getting there. It's still the same signal, but it's now been delayed. So what do they always say? If your signal, if you're using a handheld radio and your signal is kind of weak,
Change direction, move where it is.
move over a little bit, right? Okay. So if we were to move, let's say back this way or forward this way or sideways, our hope is that one of those directions would be such that this path doesn't change a lot, but now the other path bouncing off of the pickup truck would now be extended a little bit or shortened a little bit, depending on where we're moving, such that the difference in path length is now such that our phases line up. Because it doesn't really matter if this one is, if it's delayed 10 wavelengths, but it's exactly 10 wavelengths, then it lines up perfectly. And that's why we do that's why we have something called multipath interference. And that's why they specifically say move over a couple of feet, because that actually changes the phases of the incoming signals with respect to each other. So you're actually and this is true if you've ever seen like if you've taken a physics class and you see these patterns. Let's say you're looking at this, you see if you're doing a physical let's say a light experiment where you see areas of dark and light, or if you let's say look into you get a polarized light reflecting off of your cell phone or something, and you see areas of light and dark, or rings of oil, light what looks like rings of light in an oil sheen. It's the same thing. It's just that those are really, really small waves and these are really big waves. It's all caused by phase differentials.
Got
All
it.
right.
If they were 180 degrees out, would that completely cancel out everything?
It depends on the amplitudes. If the amplitudes were equal, you'd have complete cancellation.
Same power, right? Strength of signal.
All right. So that's our heavy math for the day.
Seriously, thank you.
I
That's
hope
bad
I
enough.
hope I hope what that does is that it makes everything else make a little more sense, because this is one of those things that, when I do the technician exam, the technician class, I really don't feel right teaching it in such big detail.
Well, if you want to scare them.
But, in this particular case, this is kind of like the fundamental to a lot of stuff that we're going to cover. Understanding phase and amplitude and phase shifting and things like that, and just even what a sine wave is, where it comes from. So if everybody's okay with a 5-minute break, I'm going to try to find that lost soul who's out on the internet somewhere and can't get a hold of me.
I'm a life rep.
5-minute break.
Sir.
Okay.
Sounds good.
Three souls are online.
Hmm.
Say, Mark Miller, can you tell us a little bit about your badges in the background there? You're on mute, my friend.
It reflects VA 115 in the Navy Air Group 11 aboard the Ranger and Kitty Hawk. Sky Raider SPADs, whole room sort of at the core of the different places and commands and stuff. Many years ago.
Okay, yeah, very good, very good. So you've seen quite a lot of activity there, huh?
23 years.
Yeah, interesting. Yeah.
It's a fascinating time. Oh, I see. Everybody can see it. I hadn't quite anticipated that. I thought I was supposed to. Okay. Yeah. Let's see. Well, what do we do here? If you see what you guys can see here, sort of the old wall there, the old spans aboard the Kitty Hawk.
Oh yeah, very good. Tell us about the aircraft that you've got there.
Oh, the Sky Raider, goodness, flying dump truck. Well, they took a B-29 engine, put it on the body of a fixed wing. That was the last, probably best piston-driven meat eater that they had before the age of jets. They kept them just into the early 70s. They stopped using them up north and started doing a lot of sandy work. Everybody moved on to the A6. I did not. But
Very
they really
good.
couldn't
What's the
replace-
A6? Is that the Warthog?
The intruder. This is Navy. Warthog is Air Force. I think it's designated the A10. But the thing could carry more than its own weight in ordnance. It had a hell of a flight envelope, but it was lightly armored considering everything, and it did not have good radar suppression or radar warning. So some of the Russian radar control larger calibers started taking out very large numbers, so they had to take them off fleet air ops and move into something with a little bit more that could take advantage of the Hawkeyes and some of the new A6 radar suppressions that were coming up.
Very good. Much of what you've just told me is above my head, but maybe literally. But,
okay. Well, they just had to retire the props because even though they had very long loiter time and could really carry a huge amount of ordnance, they didn't have good protection, against some of the more modern weapon systems coming out at the time. So they pretty much had to retire them, and everybody moved into jets and using electronic warfare a lot more.
Right. Yeah. Okay.
Okay, I made it back.
All right.
We managed to grab a couple more people who were a little bit lost. So, all right, everybody ready? We're going to start with this thing called electrical principles. So we are looking at, in the book, what I have as page 3 on my electronic page in my electronic book. So what we're going to do, notice the very first thing they're talking about here is this thing called reactance. So we've got this thing called resistance, which is letter R. And then we've got this thing called X. See, we just added something, which is resistance is the opposition of flow to DC current. Reactance is the opposition of flow to AC current or alternating current. If we were to draw this current, we would find that DC current always flows in the same direction. So this is a plus or a minus. AC looks like this. Okay, so reactance is the opposition of flow to alternating current. Now, everybody, DC is very boring, right? What's the frequency of DC?
1.
It has 0. There is no frequency, right? It's always the same. What do we know about AC?
Shifts 180, or it goes through a cycle of 360.
60 cycle.
Well, it could be 60 cycle. It could also be something else, right? What do we know about AC?
It phases, it oscillates.
It has a
the range.
phase,
Yeah,
and right? It has a phase and it has a frequency, right? And what do we know about these things, phase and frequency? Are they always the same?
No.
They are not. Okay. So now this is really important because if I were to draw this device, does everybody remember what this device is called?
Capacitor,
Capacitor. How about this thing right here?
transformer.
Well, it's an inductor. It's half
I'm
of a
sorry.
transformer.
Doctor, yeah.
All right. So we have a capacitor, which is 2 parallel plates that are made of metal that allow a voltage to separate, to form on both sides. This is an inductor. And this basically stores electrical, it stores energy in a magnetic field. When you push current through it, you end up with a magnetic field that forms around it. Right? An electric field in a capacitor stores energy inside the 2 different plates. So you have pluses and minuses here. And so you have 2 different energy storage devices. You have a capacitor and an inductor. They operate in different ways. It stands to reason that when you change frequency, they might behave differently. And in fact, they do. The reactance of both of these devices, a resistor is boring. We're going to draw a resistor up here, right? Resistor is going to have the same resistance to AC as it does to DC. It's measured in ohms. A capacitor or an inductor is going to have a resistance as well, but more importantly, it's going to have a reactance, also measured in ohms, to AC, which is going to be differing depending on what you're feeding into it. So if I were to draw if I were to write out the equation for reactance of a capacitor, reactance of an inductor, that would be the big letter X, and with a sub C or a sub L, depending on whether it was capacitive or inductive. And for an inductor, it's going to be 2 pi FL. So 2 pi times the frequency. And for a capacitor, it's actually going to be 1 over 2 pi FC. Okay, so there's that 2 pi F again. This is also known as omega, which is the angular frequency. So notice that 2 pi, that's the number of radians in a circle. If I were to draw a circle, I could say that it's all the way around is 360 degrees. I could also say that it's 2 pi radians. I could go into the detail on that, but we don't have to do that unless people really want to. But anyway, angular frequency. Most importantly, once we take the 2 pi and we just put it in there, pi is a constant. Pi is 3.14159265535 and goes on forever.
Stop
and ever,
embarrassing us.
Yeah, it goes on forever. But what is interesting about this is that we now have the capacitance and the inductance, and we also have this F. So what we find from this is that our reactance is dependent upon the frequency that we're punching into it, because we have that term of F. So let us look at the extremes. We're going to take F equals 0. That would be DC. So what would be X at that of a capacitor if that's true? What's 1 divided by 0?
0.
It is not 0.
Oh, sorry.
All right. So we have X is infinity ohms. So basically what that means is if you try to push DC into a capacitor, kind of makes sense. What we end up with is infinity ohms. In other words, you charge it up and it stays charged, and then you can't put any more current into it, because that's really what it means. All right, so let's take a look at an inductor. If we take frequency of 0 and we put 2 pi 0, what do we get? Anything times 0 is 0 ohms. Well, it's just a piece of wire. We push DC current through a piece of wire, the current flows. Makes sense. Let's look at the other extent. Frequency is equal to infinity, the highest frequency we can imagine. Okay, so what's for a capacitor? 1 divided by infinity is 0. So for a very, 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 very high frequency, essentially the capacitor, the electric field is shifting so fast that it's like the capacitor is not even there, which we kind of know to be true. As soon as we build up a charge on one plate of the capacitor, we switch the power supply and the current flows the other way. So it's like the capacitor isn't even there. However, for an inductor, 2 pi FL, so 2 pi times infinity is infinity ohms. And what happens here is that we can see over on the left-hand side that the inductor, when we build up a magnetic field, it's got a magnetic field, and that's energy. If we try to switch the direction of the current, is going to be fought by the magnetic field that's already there. Inductors inherently don't like to have their magnetic fields changed, which means that it's going to resist like crazy against that, which is the same as having, infinite resistance. It's trying super hard to not let something happen. So I'd say we got it right. So now what we're going to do is go to that very next step. And this is where it's a little bit of a leap of faith. And this comes from some of the more complicated math, but basically what we end up doing with this is that we have a resistance, and we're going to put this on the x-axis. What used to be the x-axis, little x, we're not going to call it that anymore. We're going to call it the r-axis for resistance. And what used to be the y-axis, we're going to call the big x-axis, which is reactance. And we're going to call this resistance. Okay, here we go. What we're going to do is say that in this case, really, we're not even going to call this reactance. We're going to call this something totally different. What we notice about this is that if we use the big letter R, and we know that this is the positive side, can we ever go on the other side of that graph? Is there such a thing in practical terms as negative reactance? There probably is in math, negative resistance. If something can anything have a negative resistance? In practical terms, the answer is no. Okay, but now we have this thing called reactance. And as it turns out, we have our positive reactance and our negative reactance. And what ends up happening in this case is that an inductor has a positive or a positive impedance. It's, in other words, it's actually, its reactance causes an impedance to be in the positive direction. And a capacitor will cause something to happen in the negative direction. So that XC causes it to go down and the XL causes it to go up. And these are actually perpendicular to each other, right? To the resistance. So if we were to draw a triangle based on this, we would find that we had a resistance and, let's say, a positive reactance. Okay, does this look somewhat familiar to that triangle that I drew at the beginning of this mess?
Yes, it does.
It does. Okay.
Yeah.
All right. Well, this is known as Z, which is impedance. And so what we end up with impedance is R plus, we'll call it little j. This is the j axis. R plus jx. And what that little j signifies is an imaginary number, but really in this case, it's not imaginary. What it actually is indicating that it's on a perpendicular axis to the resistance. Well, if it's on a perpendicular axis to the resistance, that also means that we can use the Pythagorean theorem to figure out what it is and find out that Z is equal to R plus JX. And this is known as a complex impedance because we can't just add R and X together because they're perpendicular. That's like saying, okay, well, what's the shortest distance between here and here if this is 4 units away and this is 3 units away? If we could just add them, we would say that that's 7 units away, except that it's really not, right? By the Pythagorean theorem, how far is that walk going to be?
5.
That would be 5. That's a 3, 4, 5 right
3, 4, 5.
triangle. That is a 3, 4, 5 right triangle. So really what that means is if I have a resistance of 4 ohms and a reactance of 3 ohms, my impedance is
5.
5 ohms. That's
5
right,
ohms.
because 3 plus 4 equals 5, obviously, right? Well, exactly. It doesn't equal 5. But what it
No.
means is that this is how far away from the origin I really am. So it is inaccurate to say that 3 plus 4 equals 5, right? It's more accurate to say that 3 plus J4 equals 5. Because the J indicates that it's at a perpendicular axis. And this 5 is not completely, it's not completely instructive either, is it? Because it doesn't really tell the whole story. The rest of the story is told by the fact that we now have this thing, which is like 4 and 3 and 5. Okay, so we know that that point is 5 units from the origin of the circle. Right? We know that we had to go 4 units of resistance to get to the right, and we had to go plus 3 in the y-axis to get there. So our reactance is plus 3. Well, if we know that our inductances are positive typically, and our capacitances are negative, we know that this is probably an inductive reactance, as it's called, that got us there. But now we can look at this and say, okay, well, how would we really explain what this point is?
How would we name it? Well, it's a distance of 5 units away, but it's turned. If this is our 0-degree axis, how far did we have to rotate this thing to get there? And to do this, we can do some trigonometry and say that our tangent of our angle is the opposite over the adjacent is equal to, here's the opposite, and here's the adjacent, 3 divided by 4, and we'll call that tangent of theta. And we can use our calculator to take the arc tangent, which is the inverse tangent of 3/4. And let me grab this and make sure I don't get it wrong. Make sure we go to scientific mode. We go 0.75 and we go, what's the inverse tangent on this? Wouldn't you know, I can't find the, there we go, inverse tangent, 36.9 degrees. Okay, so we know that the impedance, which we call Z, which is something which would be a complex impedance, would be 5 units, right? That's the amplitude, with an angle of, let's say, 37 degrees. That would perfectly describe that point. And we know that because it's above the horizontal axis, we know that it's a positive reactance. And we know that it has some resistance because it's shifted off to the right. So if we had this impedance, the cool thing about this now is that we can actually take a special case. The special case is, let us look at a plain old resistor. So we're going to look at our plain old resistor, which is a boring thing. Let's say R is equal to 4 ohms. What would be the reactance of a plain old resistor? How many ohms? Does it have any capacitance? No capacitance. Does it have any inductance to speak of? Maybe a little. Tiny little bit, but none really to speak of. So does it have any reactance at all?
Say yes.
Let's give it a pass. We'll basically say it has none. So our reactance of our resistor is 0 ohms. Well, we can write this for an impedance of Z is equal to R plus JX. So what is our impedance? 4 plus J 0. So in this case, it's just 4 ohms and it's real. There's no imaginary component. There's no reactance to it. So for a resistor, our resistance is equal to our impedance. Does anybody have a dummy load?
Yeah, I do.
Okay. When you buy a dummy load, what is the dummy load supposed to be? How many ohms?
I'm matching 50 ohms to the antenna.
50 ohms. Okay. A dummy load is built as having a Z, which is an impedance, right? Because we're talking about radio. Radio is AC, 50 ohms. So if I were to actually write that out, ideally that would be 50 plus J what?
X.
J0.
Oh,
In other words, it has no reactance component. So
it's just 50 ohms.
It's just 50 ohms, purely resistive. Now, when you build a dummy load, they specify, do not do a wire wound resistor. Why would you not want to do a wire wound resistor, which has a lot of heat dissipation capacity because of how it's built?
Big magnetic field.
That's
Yeah,
right. It would
magnetic
have a
field, yeah.
magnetic field. If you have a magnetic field, what do you know about the impedance? What do you know about the reactance of an inductor? Is it 0?
No,
It is not 0. So
but
your
have a lot of
new,
resistance.
it'll have some resistance and it'll have some some reactance. So what that means is that your dummy load will now, if you build it that way, have a resistance of 50 ohms plus J something.
So impedance.
And what's the formula for that? 2 pi FL. Okay, well, you've specified what your L is because of how you picked it. What's the one thing you can't pick?
Frequency.
Frequency. So what would that mean for your dummy load if you built it the wrong way?
You'll be putting out a signal.
Well, not only that, what would your total impedance be? It would change based upon the frequency that you're using it at. How good of a 50 ohm dummy load is that?
It's not.
It's not. That's right. Because now you don't know what the impedance is. And not only that, it's not stable because when you're testing out your transmitter on 80 meters, your impedance might be 50 plus J 5 ohms. When you're testing it on 80 meters, it might be 50 plus J, or let's say when you're on 40 meters, 10 ohms. It's going to be different. And in fact, if you were to then try to figure out what the magnitude is, you'd have to draw the triangle and say 50 and 10, and it's actually something closer to 55 ohms. If you went to 10 meters, it might be 75 ohms. What's your transmitter looking for? How many ohms?
50.
50 ohms. This is not a good piece of test equipment anymore. And that's why we don't build it that way. So the other thing that's important is that we're going to get to something called impedance here. And let's say that you have an impedance which is, let's say 4 ohms plus J 3 ohms. I keep going back to that because it's really easy to work with. So we know that this is 37 degrees. So our impedance is 4 plus J 3 ohms. It's also 5 times angle 37 degrees ohms. If we wanted to actually split this out, this angle 37, it could be, it would actually be cosine of 37 plus J sine of 37 degrees. Well, it turns out that that gives you exactly the same as that. So this is a shorthand method of writing it. So now let me ask you this question. What is Ohm's law, everybody? What is Ohm's law?
E equal I times R.
E equals I times R. But is that exactly right?
No.
No, it is not, because it's not R anymore. What is it?
It's inductance.
It's a big letter Z, which is impedance, right? So if I were to draw this and say E equals I times 5 times angle of 37 degrees, what would happen if I put a current into it? What would happen to the resulting voltage?
Would drop.
What would happen?
Increasing resistance.
Yeah, well, here's what I'm going to do. If I were to draw my current right here on this XY graph, all right, and I say that my current was 1 amp, and I go through this formula, what would my voltage be? Just multiplying 1 times 5.
It's on the same voltage.
Right, well, it would be 5 volts, right? But what's this annoying 37-degree thing doing here? What does that result in? What does what happens up there?
You encounter inductance on these.
What would happen to that? What happens to that angle? I mean, what's the
Increases.
function of that angle? It's to rotate something.
If you're adding more power, won't it rotate up?
Well, it's not power. It's just what the math says, right? It's
Angle of degree?
an angle in degrees.
Yeah.
So what that would do is it would take this red line that we just drew, which is voltage, and it would rotate it up 37 degrees. Okay. This is actually really, really important and really profound, because what does this mean? If something is now rotated by 37 degrees, what is this? And what is that triangle a graph of? What's it another way to show? Does everybody remember about half an hour ago when we drew this?
We're changing the phase of the signal.
Changing the phase. You're actually changing the phase of the signal, which now means that if I were to draw the current and it looks like this, and this has an amplitude of 1, my voltage would have an amplitude of 5. Everybody agree with that? Because we looked at this 5 times angle of 37 degrees. So the amplitude would be 5. But there's that angle of 37 degrees. Well, this is 180, that's 90, 37's about here. Our voltage would do this. And if I were to measure the phase difference between the two, what would I find?
Would be your frequency?
Nope, the frequency is the same. That never changes.
Oh, okay.
I would measure a phase difference of 37 degrees. In other words, if I have a complex impedance, which has a reactive part, what we will find is if it's a positive reactance, like we just showed right there, because it's above that horizontal line, it will cause the voltage to be ahead of the current when I measure them. It will actually cause a phase shift of the voltage in the positive direction. So in this case, voltage leads current.
In the real world, what would that cause?
That would cause a phase shift. And in fact, this is really important because what's the other part of Ohm's law? The power part.
Oh, pi.
P equals I times E. Okay. This is only equal to I times E when the phases are in phase, when the things are in phase with each other. You agree with that? If I were to actually try to figure out the power, the actual power, what happens if these things are now out of phase? Because you basically are multiplying two things that are now shifted off of each other. Ever heard of something called reactive power or oh heck, I'm drawing a blank and I shouldn't. Power factor. Have you ever heard of something called power factor? Okay.
Strength of something.
If you have a motor, the power factor.
The power factor is is the cosine of the angle created by the device. If something has a power factor of 1, that means that the current and voltage are perfectly in phase with each other. The power company finds this to be really important because they still have to deliver the same amount of current and voltage, independent of what you're doing. But if they're not lined up, they still have to deliver it, but you're not really using it, which essentially means that you're wasting their energy. You're wasting their effort. So they do something called power factor correction. So if we know that an inductor, because this is an inductor that's causing this power factor, we know that because the reactance is above the horizontal line. This would be an inductor. That's inductive reactance. Okay, if we know that to be true, and that is causing this to happen, what would take this positive part and pull it down? What device would take that plus part and pull it downward?
Add a capacitor.
That would be a capacitor. So if we were to take this thing and add a capacitor so that it completely nulled out the vertical change, what we would find is that this would now be shifted over, and at a given frequency, you could actually put them back in phase. And this is why, if we're building an antenna, for instance, sometimes we will have this. That is why we will put a capacitor somewhere in an antenna. That's why we'll put an inductor somewhere in an antenna. If we're tuning it for a given frequency, and we know that our impedance is inductive right here, looking at the outside, we can add a capacitor to cancel out the inductive portion. If we have a capacitive thing, we can add an inductor to cancel out the capacitive portion. And what we end up doing is taking this right here and shifting it by this much, so that the vertical portions cancel each other out.
And that's why they want a 1-to-1 on the antenna ratio SWR.
Yep. So this is the magic that allows all this stuff to work. And everything's easy from now on. But this is a good time to ask questions.
How will we actually apply this when it comes to what we're doing, unless we're building an electronic set or something?
Well, if you're building an antenna, so let's say that you have an antenna analyzer, right?
Mm-hmm.
You're building an antenna, and your antenna analyzer says that your antenna has an impedance of 70 ohms.
Okay.
Now, what does that mean?
You gotta bring it down to 50.
Well, you don't know. This could be a couple of different things. This could be 70 plus 0 ohms, or J0, which means that if you were to draw it on the graph, it would be over here, which means you have too much resistance. There's not much you can do about that. Or too much essentially antenna resistance. What are you going to do with that?
Antenna tuner on it?
Well, potentially, yeah. But now you've got another issue here. Let's say that instead of 70 ohms purely resistive, it's actually 40 ohms plus J 50 ohms. And it still gives you 70 ohms. Right? But on the graph, this is now way up here. The amplitude is exactly the same, but it's in a totally different place. Knowing that information, you can say, okay, do I have an inductive load or a capacitive load? Which one am I?
You want an inductive load to bring it in.
So we are, if we are above, up here, we are inductive. And if we're down here, we're capacitive, right? So what do you use to cancel out an inductive load?
Capacitor?
Capacitor. If
Yeah.
it was instead 40 ohms minus J 50 ohms, which would be down here, what would you use to cancel that out?
Inductor.
You'd use an
Yeah.
inductor. That's exactly right. And and if you're choosing a particular frequency, that's how you pick the value. And that's why knowing what complex impedance is really important.
So
Because-
question around the exam.
Yep.
How many questions are going to require us to remember, you know, the various algorithms and equations to figure this stuff out, right?
You really only have to remember two things. XL is 2 pi FL. And XC is 1 over 2 pi FC. Those are the really important things that you need to know. And to understand that because they're frequency dependent, if the frequency shows up in the numerator, like for an inductor, what happens if the frequency goes up? Then the impedance will go up. The reactance will go up. If the frequency goes up in a capacitor, the reactance will go down.
Say
So,
that again.
well, it's just applications of these right here.
Yes, but you just phrased it correctly, and I need to get that down.
Okay, well, let's ask this. Like, there's actually a question. In an inductor, if the frequency goes up, what will happen to the reactance? It goes up. Because you wrote the equation, and if you got them right, then you know that it works. If the frequency goes up in a capacitor, what happens to the reactance? It goes down because your denominator got bigger. So these and these are the fundamental parts of how all this stuff links back together. All right. So now that we have established all that, those are the fundamental things that you're going to have to remember with regard to the complex numbers. And it's all cake from here on. Okay, so what are the units of impedance? That's right. What's resistance measured in?
Ohms.
What's reactance measured in?
Ohms.
That's right. They're all ohms. Okay. So let's see. We are actually now on page 4 in the book. So what happens if the impedance of an electrical load is matched to the impedance of the device, like the radio that you're putting power out of?
Get maximum power.
You get max power. That's right. That's the point of matching your impedance. Okay. What's reason to use an impedance matching transformer?
Match the internal load.
That's right. It matches to the load, and if the load is matched to the source, that means you can deliver maximum power. All right. Let's see. Different ways of matching impedance. You can use a transformer, which we're going to get to. You can use a pi network. A pi network can look like this. Anyone guess why that's called a pi network? Pi spelled Pi.
Yeah,
Greek letter pi. Looks like a Greek letter pi. That's why that's known as a pi network. Or a length of transmission line. So as it turns out, any transmission line of a given impedance can act as a transformer as well. Let's see. For matching impedance between two AC circuits, let's say we have an AC circuit that's 30 ohms and another one that's an AC circuit that is 2000 ohms. So what can we do about this? We can add, for instance, an LC circuit. Or an LC circuit that looks like this. We can add it basically a number of different ways. So an LC circuit is used to match two different impedances together. Okay, now we're into decibels and voltage dividers and stuff like that. Okay, everybody remember what a voltage divider is? Okay, so here's our voltage. That means we're going to cover a voltage divider. R1, R2. Okay, so this is a series connection of resistors, R1 and R2. So if I have a voltage V, actually I'm going to use, I'll use V. What do we know about the current that flows out of here compared to the current that flows through the resistors?
That's current derived in that.
It's going to be exactly the same, right? Okay. And by Ohm's law, what is V1? You know, I'm just going to use E. I like E better now. We'll stay with the program. Okay. If this is I and this is I, E1 is going to be I times R1. E2 is going to be I times R2. Well, these resistances are exactly the same. And we know that if we start at one point in a circuit and we go all the way around, we know that E is equal to E1 plus E2 is equal to I R1 plus I R2. It's equal to I times R1 plus R2. And that is how we know that resistors add when they're in series. Well, we also know that in this particular case, each of those resistors is going to have a different voltage measured across it. It's going to be less than the source voltage E. This is known as a voltage divider. So let's say this was a 10 volt source. I could pick my resistors so that I have 3 volts here and 7 volts here. So that would be known as a voltage divider circuit. A current divider, if I wanted to actually split my current into two pieces, I could have my battery here and have a resistor here and a resistor here. Okay, so if I have a voltage E, what voltage will be experienced by this resistor right here? R1. Everyone?
E.
It's voltage E. How about by resistor 2?
Same.
Same, which is E. So what will happen to the current, the full current I? It will be split. It will be split by the resistor itself, by the size of each resistor. So this is known as a current divider. And actually, this is known as Kirchhoff's current law, which says that the sum of all the currents going into a particular point has to be equal to the sum of all the currents going out of the point. So if I were to take this node right here, as it's called, that would mean that basically all the current going in has to be equal to the current going out. Okay. Next, we're going to do something called RMS. Okay. Let's say that I have an AC voltage that looks like this. And the voltage goes from V peak to negative V peak. It's a symmetric AC voltage. There's our zero. Okay, so now let's say that I have a voltage of 170 volts and negative 170 volts. Does anyone know why I picked these?
US standard.
Yep, that's a standard that we're going to see. Okay, so this thing is also a sine wave, right? That's a sine wave. Okay, so let me ask this question. By Ohm's law, what is the power at any given point? What's the formula for power, everybody?
Or pi, power times current times voltage, or current plus voltage.
I times E, exactly. Well, we can also rewrite this because E is equal to I times R. It's also equal to E squared divided by R, whatever that resistance is. So power is equal to E squared divided by R. So let me ask the question. In an instant in time, what is the power dissipated, delivered right there when the peak is at 170 volts? Well, it'd be 170 squared divided by R, right? That's a lot. How about down here? That'd be negative 170 squared divided by R. Even though the voltage is negative, those two are equal, are they not? How about right here at where it's zero? What would be the power delivered right there?
Full power, no resistance.
It'd be zero. And it'd be zero right here too. And zero and zero and zero. Well, so basically what this means is that in order to figure out how much power is delivered to a circuit by this voltage waveform, we actually have to know what it is at every point and then average it out. Well, as it turns out, this is actually a mathematical thing. And what we do is we take the integral over one waveform, 0 to 360 degrees of V squared over R dt divided by the time or by the phase.
And D stands for what, distance?
Which one?
What does D stand for, distance or what?
Well, it's integral calculus. So what we're going to do is avoid the calculus altogether, because this is V squared of T dt by 0 to big letter T divided by T. Essentially what this is a time-based average. And it turns out that then you have to take the square root, because it's the root mean square. So you have to do one of those. And this gets kind of ugly to solve. So we're not going to do this. But this actually is the average power delivered. And this is known as the RMS, which is called the root mean square. And what that is an equivalent voltage in DC that would deliver the exact same amount of power as an AC circuit. Well, this thing that I drew, which has peaks of plus 170 and minus 170, is also known as 120 VAC. Anyone recognize that?
House current.
That's house current. That's right. So if you were to stick in your RMS reading voltmeter, you would see that you have 120 volts in your wall circuit. Well, if you were to take an oscilloscope, which measures amplitude or voltage versus time, you would see that you have a peak
of 170 and a negative peak of negative 170 volts. You would see this waveform that is much larger. The reason being that you have, for a sine wave, a factor of about 1.4 times the peak. So importantly, this means that if we have a signal that is 12 volts RMS, that means that we are going to see 12 volts times 1.4 approximately, or about 17 volts peak. It also means we're going to see negative 17 volts negative peak. So if we were to measure the peak to peak voltage and put it on an oscilloscope, how many volts would we see roughly? From plus 17 to negative 17. How many volts would we see total? 34 volts. That's known as peak to peak voltage. So if we were to do our wall voltage and say that we have 120 volts RMS, what would our peak be? About 170. What would our negative peak be? About negative 170. So what would our approximate peak to peak voltage be?
340.
About 340 volts. And in the book, it says 339.4. To me, that's about 340 volts. And that is why we have something called peak to peak voltage. Okay, so now we're going to do a little bit of Ohm's law stuff. Okay, so I'm on page 7 of the book. Let's say we have 400 volts DC and an 800 ohm impedance, right? Well, we're going to say that it's pure resistive. It's 800 ohms resistive. All right, okay. So what does Ohm's law say? Power is equal to what? We got power is equal to I times E, and E is equal to I times what? Well, we could say R, it's really Z, but in this case, we're going to say that it's R because we already said that it's resistive. So we can do this. The first part, E equals I times R, 400 equals I times 800. We calculate that I is equal to 1/2 of an amp, and then use the power. P is equal to 1/2 of an amp times 800 ohms is 400 watts. And in fact, I believe, did I get that right? 400 volts. Oh, whoops, it's not 800. Nobody caught me. There we go, 200 watts. Okay, so now that means for VDC. So what if we replace that voltage with something that was 400 volts RMS? What would our power be delivered through the same resistor? It would be the exact same thing. Because what is the meaning of RMS? RMS is the equivalent voltage that delivers the same amount of power as a DC voltage. So if something has a voltage of 400 volts RMS, that means it can do the same amount of work. It can deliver the same average power as a 400 volt DC voltage. If I were to say that my voltage was 120 volts RMS,
the equivalent DC voltage would be 120 volts DC. Now, another thing that's interesting about this is if I were to draw this thing, what is this wave called, everyone?
Sine wave.
Okay, if I were to draw this wave, what is this called? I didn't square that off very well. What is this wave called? Anyone?
Square wave.
That's a square wave, yeah. So let me ask, when this is at its peak up here, I'm delivering peak power. When this is at its peak down here, I'm delivering peak power. What happens when I'm at the 0 points? How much power goes through?
0.
0, okay. How about with a square wave? When I'm up here, am I delivering peak power? Yep. How about when I'm down at the bottom? I'm also delivering peak power because it's the voltage squared, and the negative, positive and negative don't really matter. Do I ever send out 0 power? Does this circuit, which basically flip-flops between high and low with no transition time, ever go through, does it ever actually deliver 0 power?
In the transition time, the answer is no.
And the transition time is almost nothing. This is known as a square wave. The transition time is very, 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 very short. So in this particular, yeah, it's constant power. So in this particular case, VRMS, is it equal to 1.4 times the peak? Or sorry, is VP is equal to 1.4 times VRMS. How about down here?
There's no differential.
Yeah, there's nothing that, it's just VP is equal to VRMS because it's not a sine wave. That factor of 1.4 is there because it's a sine wave. If it's a square wave, they're exactly equal.
That brings up the question of what produces a square wave.
What produces a square wave? Digital logic, transistors.
No gap in power.
Hmm?
No gap in power with a transistor.
It depends how it's done. This is why certain things are better at delivering power than others. This is why certain waveforms are better at delivering power than others.
Would that then infer that an SDR radio can be more consistent than a regular VHF radio?
No, I mean, when we're talking about power, what this actually means is this waveform at the bottom could be construed as, let's say, something that is like a class C or class D amplifier versus something up top, which would be class A, for instance. So yeah, I mean, like for instance, a class D amplifier or a class E amplifier that runs in saturation is actually much more efficient at delivering. It's got tons of distortion, but for certain things that you're trying to receive, it doesn't matter. That's why people use it. For certain things, it does matter. I mean, if you're trying for, replication of an analog signal, you wouldn't use a class E amplifier. But for FM radio, it might be fine. Okay. Let's see. We're gonna do another RMS thing. I'll just pick one here. Okay, 50 ohm dummy load. Okay, what is the resistance of a 50 ohm dummy load, everybody?
50 ohms.
What is the impedance of a 50 ohm dummy load?
50 ohms.
Plus J 0 ohms. So if I were to draw this on the graph, it would be 50 ohms here and 0 ohms up and down. That is a nice, perfect dummy load. Okay. Now, let's say that with this 50 ohm dummy load,
We had a power dissipation of 1200 watts. It's a lot of power. Okay, so what would Ohm's law allow us to do here? E equals I times R, P equals I times E. And in fact, we're going to replace R with Z. All right. So what we're going to do is we're going to take this right here, and we have our power right here. So we're going to substitute E. Let's see, what was the question? What would be the RMS voltage? Okay, so RMS voltage, which means we're going to substitute current. So I is equal to E divided by Z, and we're going to plug it in there. P is equal to E divided by Z times E is equal to E squared over Z. Well, we've got our impedance of 50. We've got our power of 1200. We've got 1200 is equal to E squared divided by 50. E squared is equal to 60,000. E is equal to 245 volts. And more importantly, what is that measurement? What is that voltage in units of? Is that a peak to peak or a peak or an RMS voltage? That would be RMS because it doesn't matter what the voltage was. Now, if I were to tell you that this was a sine wave with an RMS of 245 and we were to graph it, what would the peak voltage be? So this is 245. And there's my sine wave. There's a factor of 1.4 times 245. And that would be, grab the calculator. 1.4 times 245 is 343 volts. That would be volts peak. I could also measure at the bottom part. I'd have minus 343. Okay, so now here's my question to everybody. Why is that important? Why is it important to know peak voltages?
Your transmitting power?
Nope.
Component voltage ratings.
Component voltage rating. Okay, so let's say that I had something that was a capacitor in my circuit, and I had 245 volts RMS and a peak, because I knew it was a sine wave, of 343 volts and another one of negative 343 at the bottom. And that voltage was appearing across this capacitor. And this capacitor was rated at 250 volts AC. What would likely happen to that capacitor when that peak hit?
Destroy it or burn it.
It would destroy the capacitor. The reason being that internally, there's a dielectric material that is designed to produce a separation of the two plates and allow pluses and minuses to form across it and create an electric field. In the process of doing so, however, this has a puncture voltage, which essentially is a function of the material. And if this is rated at 250 V, it's really rated at 250 volts, for instance. So let's just make that a 250 volt material. They don't specify whether it's AC or DC. If that suddenly saw 343 volts across it, what would happen is you would basically get this avalanche of too much voltage jumping across the material and allowing this cloud of smoke to arise from it and the capacitor would likely get really hot and turn black and then not work anymore.
It's called the O shift condition.
Yes, you would let the smoke out of it. And smoke, as we know, is the magic stuff that's inside all electronic components that make them work. Okay, let's
Because it
see.
comes out.
Yeah, you let all the smoke out and it doesn't work. All right, we're almost to another break. What we're going to cover now is PEP, which is peak envelope power. Okay, so let's say you have an unmodulated signal. The peak envelope power for an unmodulated carrier. All right. So unmodulated carrier, peak envelope power. Let's say that you have a PEP reading watt meter. If you have an unmodulated carrier, if something is modulated, that means that the signal might look like this. It gets bigger and smaller. If it's unmodulated, it's always running at peak power. So if it's an unmodulated carrier at RF frequencies, that means that you have a 1-to-1 ratio of peak to average power. It's always running full. So if you have a PEP reading watt meter or peak envelope power that says that you're transmitting at 1060 watts. So what would your output PEP be if it said that it was reading 1060 watts? That would be 1060 watts, no matter how you measure it. Okay, so now let us say you have an oscilloscope measuring 200 volts peak to peak across a 50 ohm dummy load. So now we're going to do a little bit of math. So we're going to say that it's 200 volts peak to peak and 50 ohms. Okay, so now we're going to draw it. This is where it's important to know. 200. Sorry, it's 200 peak to peak. That means that at its top, it's 100. And at the bottom, it's negative 100. All right. So this is 100 volts. And that's 100 volts. And it's 50 ohms. Okay, so if this is a sine wave, what would be the RMS voltage right here? We know that VP is equal to V RMS times 1.4. So this is about 70 volts. Okay. Ohm's law, P is equal to E is I times E.
Sorry? Be careful if it's somehow it managed to spill something out. Oh, it's leaking. So you have to tip that back into.
And E is equal to I times R. So if that's true, we know this to be true, and we have 70 volts RMS. We have a 50 ohm dummy load. We know that E is equal to I times R. 70 is equal to I times 50. I is equal to 1.4. And then P is equal to I times E is equal to 1.4 times 70. And I believe I get 100 watts. So that's how you would use a voltmeter or an oscilloscope with a signal trace to figure out what your actual power was. Okay. Another one to do is, here we go, half power levels. Okay. This is actually really important to know. And you did this on your technician exam. There are two things that you need to know as far as decibels. 10 times is equal to how many dB?
10.
10, okay? And 2 times is equal to how many dB?
3.
3 dB, very good. Okay, so if I were to draw power and look at something that looked like this, and this is maximum power, we'll call it full power, where would I mark my half power point? All right, so this is 1/2 power. All right, so if I were to mark that, this would be known as my half power point or my 3 dB points. This is actually really important because if this was a filter, this is how we would indicate what the bandwidth of the filter is. The bandwidth of a filter or any device is measured by its 3 dB points, which are its half power points. So now we also are covering, oh, look, they finally gave the logarithm formula. Okay. So that's where that comes from. I guess I'm now permitted to use it. The decibels are equal to 10 times log base 10 of P2 over P1. So by looking at this, we can now, does everyone understand logarithms or do you want me to explain it? Don't be embarrassed if you don't know logarithms. Let me know, because there's probably other people who don't also.
I'm not embarrassed. Can you go ahead and explain it?
All right, here we go. We're going to take the time to do this because this is all about learning. All right. So a logarithm is, if you think about your, let's say, think about your earthquake scale. An earthquake, an earthquake that's a Richter scale of 1 is no big deal. A 2 is a lot bigger, but still small. A 3 is bigger. 4 is a lot bigger. 5 is huge. 6 is really, really big. 7 is incredibly destructive. 8 is everything's falling down around you, right? Well, what that means is those are orders of magnitude. So what that basically means is that the actual strength of something is 10 to the whatever that we're measuring in. So if something is a 1, that means it's 10, which is a value of 10. If something is a 2, that means it's 10 to the second, which is 100, and so on and so forth, all the way up to the 8th. Well, that is clearly a lot bigger. So basically, this exponent that we use up here, the whatever, is the measure that we give to something. So that is an exponential growth. The logarithm, for instance, is what we actually have to do to get to that point. So it's sort of like the opposite. So if let's say we had 1,000 is equal to 10 to the something. Does anybody know what that is offhand?
10 to the third.
That'd be 10 to the third. Okay, so the reverse of this would be the log base 10 of 1,000 is equal to 3. It's the inverse of doing an exponent base 10. This basically says, to what power would we have to raise 10 to get 1,000? So decibels are 10 because of deci, it's a factor of a tenth, times log base 10 of some compared thing to some other compared thing, a reference point. So let's say we lose, excuse me. Let's say we measure our power at 2 different points in a transmission system. Going out of the antenna, we measure 50 watts. Going into the antenna, we measure 100 watts. The question is, what would our loss be in that antenna system? Well, this is our power at our second point. This is our reference point. So the question is, decibels is equal to 10 times log base 10 of 50 divided by 100, which is actually 1/2. So now the question is this right here, log base 10 of 1/2. That means to what power do we have to raise 10 to get 1/2? And this is something that you can't easily do without, a graph or without a calculator. But this is why we know that it turns out that 10 to the negative 0.3 roughly is equal to 1/2. Well, as it turns out, now we know that this is negative 0.3 approximately. 10 times negative 0.3 is negative 3. So if we cut our power by a factor of 1/2, that is a loss of negative 3 dB. If we raised it by a factor of 2, let's say we had an amplifier in here, and instead of 50 watts out, we had 200 watts out. Well, our power would now be, instead of measuring 1/2, we'd now be looking at 2. And we know that it turns out that 10 to the 0.3 is equal to 2. And we know that that becomes positive 3 dB, approximately. If we were to do this, and we said, okay, we got a power of 1,000 watts out, we would do the math again and say, okay, this is now 1,000 divided by 100, which is 10. All right, so now we look at this. What power do you have to raise 10 to get 10? Everyone?
Yeah.
That'd be 1. 10 to the first power is 10. So this would be 10 times 1 is equal to exactly 10 dB. And that's why a 10 times fold in power gain is equal to a 10 decibel gain. So now, once we have that, we can say, for instance, if we have a loss of 1 decibel in a transmission line, that would be -1. I think everyone would agree with that. So -1 is equal to 10 log base 10 of something. We're trying to figure out how much this actually goes down. So now we can sort of rearrange this, put the 10 over here. -1/10 is equal to log base 10 of the something. And what did we say the inverse of doing a log is? Can raise both sides. We can raise both sides to a power with the base of 10. 10 to the -1/10 is equal to 10 to the log base 10 of the question mark. And this is an inverse, so that we basically just get question mark is equal to 10 to the -0.1, which is about, grab the calculator, 0.1, and we go 10 to the x, and we get 0.79. Okay, so the question is let's see, page 9 of the book, the question is, how much power do we lose? Well, we know that this is the power that's left. Well, if that much power is left, how much power did we lose? Roughly 0.21, or about 21%. Because we have 79% remaining of whatever power it was that we put in.
which is why decibels are very useful. All right, is everybody ready for a break?
Brain drain.
Brain drain? Okay, good. Well, it does get easier. You got questions? This is an open discussion. You know, this is kind of like the way I run this is that everybody, unless you tell me otherwise, the assumption is that people have the baseline knowledge. But if you don't, there's benefit in talking about it. So that's why I said, when does the class end tomorrow? The class ends when it ends. If everybody's good with it, then, we're done. Go ahead, Russ.
Kind of a non-radio question, but we talked about inductance of running a motor and the desire of a power company to have a total reactance load and not lose it through inductance.
Yep.
A motor like a pool motor, maybe 1 to 2 horsepower, has a capacitor, which largely I thought was used to help start it.
That's because it's a single phase motor.
Okay. Does some part of that inductance stay in the line to make the power factor 1 of the motor to the power company?
Typically, the power company isn't going to care for a motor that small.
Okay.
And yes, I mean, it is possible to have power correction capacitors even with a small motor, but again, the power company is not going to typically care.
All right.
And where they really care is, let's say that you run a paper mill and you have a 400 horsepower motor.
Understand.
And let's say they have that 400 horsepower motor, and the start, it takes, when it's starting up, the power factor is really, really bad, and they have to deliver just gobs and gobs of current to it. Even though you're not using the power, they still have to deliver gobs and gobs of current. So if let's say that you have a motor that pulls 250 amps.
Okay.
However, if you were to do power factor correction or start it more slowly, you could actually get away with pulling 100 amps.
Okay.
Okay. How much current does the power company have to deliver to start a motor that pulls 250 amps?
1.4.
Yeah, well, it's 250 amps.
Oh, okay.
But if you can drop it to 100 amps, how much current do they have to deliver?
200. I'm
No,
sorry,
it's
100.
only 100. All right. What's the difference in cable size between a cable that can deliver 100 amps versus 250?
And the switches, right.
And the switches and all Now, the other question is, when they're doing that, how can they sell the power to anyone else? Can they sell that current if they're delivering it to you? They can't sell it to anybody else. They have to make it, and you're not really using it because you don't need it to make the power. You just need it to be there. So for you as the end user, the power company it's better for you, but it's really better for the power company, and the power company will tell you that by giving you a big discount.
Okay.
Because they don't have to deliver it. They don't have to put in the infrastructure.
And this is why they, on higher horsepower motors, they want to go to 3-phase.
Well, 3-phase is the beginning of it. They start easier, they're easier to, and they always run in the right direction. But there's power factor correction on 3-phase motors too. I mean, if you think about it, a motor is the way that a motor makes torque is by being inductive and having inductive reactance and having the voltage lead the current. That drags the motor forward.
Okay, I'm gonna drop the question because I think it's off the subject. And you've
no, I'll talk about it all day. I do this at work.
I'll talk to you offline with an email or something. All right,
well,
bye-bye.
I actually do this at work. That's part of my job. It's a lot of fun.
Okay,
actually.
all right. In one sentence, tell us what you do at work.
I build I build factory automation equipment.
Good. Okay.
Yeah. So. All right. Any other questions before we get a couple minute break?
It's not a real quick one. Would you
Yeah.
mind showing me the math again on how you get your RMS? You had 100 and then 70 was the RMS. Do you mind showing me that
Sure.
math?
Okay. Well, the math is, I mean, I'm not going to do the calculus, but I'm going to do this. Is that all right? Okay, if I just do the graph.
Yes.
Okay. So if I have VRMS and a sine wave, the peak is VRMS times 1.4. That's it. And that's because it's the average power delivered over a period of time, over an entire cycle. And that's why because it's delivering more power at the peak than it is at all other times. So if you were to average it out, it produces the same amount of power as this flat line.
I'm confusing myself. If you had the peak, how do you get the RMS?
If you have the peak, let's say you have a peak of 100 volts, and then V peak is equal to VRMS times 1.4, and you have this, then VRMS is equal to VP divided by 1.4.
Thank you.
Yep. So that would be about 70 volts in this case.
Thank you very much. I needed that.
Okay. Potty break. All right. Other questions? No questions. Wait, Russ, I see your mouth moving. Russ, I see your mouth moving, but you're muted. Either that or I'm going deaf.
Okay. As my wife says, when I go get a cup of coffee, I don't think you're talking to me. And I said, no,
okay.
but you understand electrical engineering. No, I was trying to take a note here. Scott, is it? Yeah,
Yeah.
Scott. Okay. No, this is quite interesting because it's reminding me of stuff I learned in school more than 60 years ago.
There you go.
I never had a chance to use since.
And just as long as I'm yakking at you, my real question is, we just moved into an addition of homes that has 17 water features, each driven by a 3 horsepower pump. And I'm trying to figure out how to make all this stuff run correctly. And I didn't know if we had an angle with the power company to do something different with the way it was connected.
Well, wait, so, how big is the pump, or each one is run by?
Each one is 3 horsepower. I'll take this offline with you in an email.
Wow.
I don't want to waste the class
No,
time.
no, that's a lot of power.
Well, it is. And it was probably put in 27 years ago to sell homes without any consideration of what we're doing. And, you know, now some of us are trying to figure out if it makes any sense to do anything differently.
Wow.
The other thing that's killing us, Scott, is that these pumps used to be able to buy them for $4,000. Now it costs $4,000 to pull them out and repair them. You know, because they're submersible. New one costs close to $7,000 today. So
that's each, right? Or is that
each.
for all of them? Yeah.
No,
Yeah,
that's each. That's we pulled 2 pumps out as an $8,000 bill.
Jeez.
And we're trying to figure out, you know, should we try 3-phase? Should we do anything differently? I mean, we're trying to do it in a cause and effect manner.
You might have trouble getting the power company to pull 3-phase to you unless they want to.
Well, they
Unless
probably
you've already
wouldn't,
got it.
and we probably couldn't afford it. But then we could buy some kind of an inverter, but that's not. That's beyond what we're trying to do. You know, it's just you don't want to get so complicated that you don't know what you're doing.
Are they all at least in the same basic place?
Yes. Well,
that's
not
good.
not within feet of each other, but within you know, maybe a 20-acre area.
No, that's not close.
Yeah. Yeah. I do have a fellow working with me that his career has been to work on building plants for Intel. Probably doesn't do the same thing you do. He probably, you know, he probably might be in project management, and we rely on people with your skills for the nitty gritty. Like he says, I don't know electrical engineering, but if I have a double E problem, I've got the double E standing beside me to help me out.
Yeah.
So on anything that I think is relevant on this, I will get back to you with an email, but I'd just as soon not take up the time of the class to talk about this sort of thing.
Okay. All right. Any other questions? I know it's a lot of material. And Ray, you've got a definite Bohemian Rhapsody thing going there. Do you notice the image?
Yeah, on the wall. Yeah.
Well, with the dark background and
Oh yeah, well, it got dark. I only have one front window, so
yeah, okay.
that changes it a lot. It gets real dark, and with the curtains, I mean, it kind of makes me look like a floating head.
Well, right. You know, you've seen the Bohemian Rhapsody video.
Yeah. Okay.
All right. Everybody ready to keep going? Resistors, capacitors, inductors, and cool stuff like that. Okay. Which of the following increases the total resistance of a resistor? If you have 2 resistors in series, they add together. So what we're going to do is put a resistor in series, R1 and R2. The total is R1 plus R2. If I were to take resistance 1 and put it in parallel with another resistor, I have R1 and R2. The end result is R1, R2 over R1 plus R2. Or 1 over R1 plus 1 over R2. If I were to take these and let's say 3 of them, then it would be this, and then so on and so forth. So that gets a little complicated. What's interesting, however, to know is that if all the resistors are exactly the same value, so let's say I have 100 ohms and 100 ohms and 100 ohms and 100 ohms. If I put 300 ohms in series, I'll get 300 ohms. If I get 300 ohms in parallel, I'll get 33.3 ohms. It will actually divide them by the 100 ohm resistor divided by the number of them in parallel. So if I put
4 of them in parallel, like this, the end result would be 25 ohms. And so on and so forth. Okay, so now one of the questions where you actually have to do some of the work on this is, let's say you have in parallel a 10 and a 20 and a 50, like this. What would be the parallel combination of those three? The way to calculate that is it's 1 over, oh heck, what is it? 1 over, yeah, it's 1 over, sorry, 1 over 10 plus 1 over 20 plus, sorry, 1 over 10 plus 1 over 50. And that, if I remember right, turns into 5.9. So what you'll find is that if you have the smallest resistor and you have lots of stuff in parallel, the sum of all of them will always be smaller. You know, the end result will always be smaller than the smallest one. And I think I drew that wrong. It should actually be 1 over R1 plus 1 over R2 plus 1 over R3 up to 1 over Rn, whatever that is. So that's your parallel resistance. And that's why it turns into this. Okay, so inductors, if we think about this, if I have L1 and L2, the end result, let's use X for reactance. These would actually add together. If I put them in series, inductors add. If I put them in parallel, just like resistors, that would be 1 over X1 plus 1 over X2. It would be that same division thing. So if I have an inductor that's, let's say, 50 millihenries, and another one that turns out it works the same way, 20 millihenries, the sum of these would be 70 millihenries. If I have 3 10 millihenry inductors in parallel, 10, 10, and 10, that's a simple division. It's 10 divided by 3 is 3.33. Okay, capacitors are the opposite. If I put here's the easy way to think about this. If you ever get confused. Okay, so you look at these two capacitors, right? What is a capacitor fundamentally? What is a capacitor? It's 2 parallel plates, right? Now, if I were to draw this capacitor, these 2 capacitors as one, wouldn't that be the same as doing this just with bigger plates? Because basically this plate is in the same place as this plate, and they would add together. And this plate is in the same place as this plate, and they would add together. That would be the same as just drawing a bigger capacitor. So that is the easy way to remember that capacitors, when they're in parallel, simply add together. That's how you can remember which is which. And it comes back to just drawing what they really are internally. So if you have 2 capacitors in parallel like this, and you have 3 microfarads and one that's 6 microfarads, what would the sum be? That'd be 9 microfarads. And if you had, let's say, 1 microfarad in series with 1 microfarad, that would actually end up being 1/2 of a microfarad, because it's 1 divided by 2. If I were to put 3 of them in series, they would basically just, you'd use the opposite math that we use for inductors and resistors. That would be 1 divided by 3 is 0.3 microfarads. So capacitors, just the math is opposite of inductors and resistors. Okay, next. Mutual inductance. Okay, so what we're going to do is we're going to, what causes a voltage to appear across the secondary winding of a transformer? We're on page 12 of the book, by the way. What causes 1 voltage to appear across another winding? Okay, so let's draw this mutual inductance. Okay, so inductance is the act of when you put a current through a coil or an inductor, it generates a magnetic field. And it has magnetic field lines that kind of look like this, all the way around like this. It looks kind of cool, kind of like the Earth's magnetic field around the Earth. All right, so a current and a voltage, really a current that causes a voltage to, or a voltage that causes a current to flow, will generate a magnetic field. Now, if I were to place another inductor inside that magnetic field, and the magnetic field were changing in time, what would happen is that that magnetic field would actually generate a current flow that would be oscillating back and forth in that inductor. Well, there's a resistance to it, so this actually would generate a voltage. So a voltage that's generating a current, generating a magnetic field, simultaneously goes all the way through an inductor that's in that space where there's a magnetic field and generates a current and a voltage in it. So we can couple these two things together by putting them at a different spot, but at a particular spot. So this can be an air coupled inductor, for instance. You know, we basically are allowing the magnetic field to exist in the air, and the second inductor is picking up the magnetic field. Now, we can also go to the next step. We can say, all right, I'm going to draw this inductor, and we're going to call this our primary inductor. And it generates a magnetic field that looks like this. And what we're going to do is take that inductor, and we're going to instead wrap it around an iron bar. All right, so what that iron bar is that it would tend to kind of focus the magnetic field and make it stronger inside the material. Well, now we're going to take that iron bar and we're going to extend it so that it goes like this. So that this iron bar, because iron is known as a ferromagnetic material, it tends to behave in such a way that it is really susceptible to the existence of a magnetic field. That's why we make magnets out of iron and things like that. What this would then do, it would take the magnetic field that we've made and tend to channel it and couple it along inside that core. This is usually, again, made of iron or steel, and it's usually made of thin plates. So what we do is we intentionally wrap our coil around something that is a ferromagnetic material to try to get the magnetic field constrained inside the material. It'll be stronger inside the material. What we then do is say, okay, well, now that we've got most of the magnetic field lines wrapped inside that material, we're going to take another coil and do this with it. And we're going to make those magnetic field lines, which are now inside that core, we're going to make them pass directly through the center of our second inductor.
which is going to hopefully maximize the amount of effect that the magnetic field then has on that inductor. Well, if we can maximize that effect, then if we put a voltage into this side and oscillate it, what happens is we will maximize the effect of the voltage on the other side. And we can actually build this thing called a transformer. This is known as a transformer, such that we have our thing called a turn ratio. The number of turns of coil on this side is the number of turns on the primary turns. And the number of turns on the secondary side is the NS. And if we generate a voltage on this side, voltage primary, we will generate a voltage on the secondary.
Okay, Scott, does
Yes.
the wire size, that would make a difference on the secondary side, correct?
Depends. We're going to get to that. We're going to get to that.
Okay, thank you.
Okay, so we have our secondary, our primary and our secondary. Typically our voltage and current come in on our primary, and the secondary is what we're trying to make out of it. And the voltage that you get is going to be proportional to the number of turns. So very simply, VP divided by VS, that's the ratio, is going to be proportional to NP over NS. So if we have a ratio of, let's say, 100 turns per turn. In other words, we've got, let's say, 1,200 turns on this side and 12 turns on this side. And we put 120 volts AC on, because transformers only work for AC. So we've got 1,212. That would mean we get 1.2 volts AC on this side, on the secondary. If we were to take a meter and measure this, we would get 1.2 volts AC. If we put in 120 volts AC on this side, the way we've built this transformer. This would be known as a step down transformer. Now, what we've done is we've changed our voltage, right? Okay, well, energy can neither be created nor destroyed, right? It just changes form. So now what we're going to do is we are going to say we have our 1.2 volts AC, and we're going to put this through a resistor of 1 ohm. All right. What is our current through here? E equals I times R. Everyone agree E equals I times R? So 1.2 volts is equal to I times 1. I is equal to 1.2 amps. Everyone in agreement there? Okay.
Yeah.
So what's our power? P is equal to I times E. Okay, so it's 1.2 times 1.2 is 1.44 watts. Okay, because power can neither be created nor destroyed, and our transformers are really, really efficient. Assume 100% efficient. They're not, but let's say they can get to 98%. So assume that we have a power of 1.44 watts. On the other side means we have to put in 1.44 watts on this side. P is equal to I times E. So we don't know our current. I is equal to E divided by P. It's equal to 120 divided by 1.44. Oops. P divided by E. I drew that upside down. I is equal to P divided by E is equal to 1.44 divided by 120 is equal to 1.2. Move it over.
0.012 amps. So almost no current. So I have 0.012 amps over here to make 1.2 amps over here. So what is that ratio right there? Did I get that right? No, I think it's right. Yeah, that's right. Okay. So I should get a ratio of 1 to 100 in current. So interestingly, we have a 100 to 1 turn ratio. We have a 100 to 1 voltage ratio and a 1 to 100 current ratio in this transformer. So here's the next question. If we were to look at this resistance, right? And now let's say that we have over here 120 volts AC. I'm going to erase some of this because it's just taking up too much room. All right, here we go. Oops, I didn't want to erase. There we go. Now, what we're going to do is imagine that the transformer isn't even there. We're going to imagine that the transformer suddenly disappeared. And all we have is the world ending right here. Whoops. The world ending right here at this brick wall. And you are the voltage on the outside, on the left-hand side of that. And your voltage is 120 volts. And you're seeing that the power dissipation and the current, you're doing 0.012 amps. Let's do Ohm's law and figure out how big that resistance looks. E is equal to I times R. R is equal to E divided by I, which is equal to 120 divided by 0.012 is equal to 10. Is that right? Let's see, 10,000 ohms. Okay. How big was the resistor that we put over here? Does anyone remember how many ohms it was? It was a 1 ohm resistor. How big does it look? Everybody's quiet. How big does that resistance look to the outside world?
10,000.
10,000. Our turns ratio was 100 to 1. So something happened in that transformer. What happened in that transformer?
Dissipated heat.
No. The transformer has 100 to 1 turn ratio. What does it do to the resistance?
It multiplied it.
Multiplied it by a factor of 10,000.
Yeah.
Which means that it actually goes up as the square of the turns ratio. So what it does is it can function as an impedance matching device. Has anybody ever heard of an end-fed half-wave antenna?
It is.
You've ever heard of one of these things talked about?
Not a lot, but
Okay, well, what I'm going to draw is an antenna. This is a dipole antenna. It's a half-wave length long. Everybody remember covering a half-wave dipole? Now we're getting into real-world stuff. All right, how long is a half-wave dipole? It's a half a wave, whatever that is. The impedance, the feed point impedance of a half-wave dipole is about 70 ohms purely resistive. So it's 70 ohms plus J0 ohms. All right. The reason that that is true is because the voltage at the end of a piece of wire changes with the current at the end of a piece of wire. So what is the current at the end of a wire, everybody?
0.
It's 0. That's right. So the voltage at the end of the wire, it turns out, is at its peak. It's at its highest point. The current through the wire is 0 at the middle and peaks in the center. So if you're looking at being able to feed power into an antenna, what is the optimum place to feed the power? Where the voltage is at its lowest point and the current is at its highest point. That is why we feed most antennas power somewhere toward the middle if it's a half wavelength long. All right, so this is still a half wave antenna. Now we're going to create something called an end-fed half wave. We're going to feed it at the end, which is really convenient in a lot of ways, because that means you can just take that and like put it up on the side of put it up in a tree and throw the other end of the other end of the wire somewhere, and it's really easy to mount, and it doesn't have any weight to it. It can be really narrow wire. Okay. At this point, right here, if this is my voltage right here, and this is my current here, which one is at its highest point at that point? At the very end of the antenna.
Would it be the current?
No, it'd be the current at the end of an antenna has to be what?
0.
0. The voltage at the end of an antenna is thus really high. So empirically, if we were to take the impedance at the end of an antenna, of a half wave antenna, we would find that by Ohm's law, E is equal to I times R. R is equal to E divided by I, but we're going to replace R with the letter Z because it's really complex. And empirically, we're going to say this is high divided by low. And what is something that's high divided by low?
High.
That's very high. That's right. Okay, so in fact, what we find is that when we have a center fed antenna, it's about 70 ohms. If we feed it at the end, it's about 2100 ohms. Well, okay, what's our cable? How many ohms is coaxial cable usually?
50.
Everyone?
50.
50 ohms. Okay, so what do we have here? What is this otherwise known as?
They put in an impedance transformer.
That's a terrible mismatch,
Yes.
right? That's a big, bad mismatch. Okay, so we're going to try to do something to fix that. And what we're going to do is we need something that will convert 50 ohms back and forth to 2100. Okay, what is the approximate ratio of that? 2100 divided by 50 is about what?
Forty to 1.
Yep, about 40 to 1.
Yeah.
Okay, that is our impedance match that we need. And we just saw that that a transformer that built like this has an n-to-1 ratio, that's its turns. The impedance is the square of that. So what we really need to get a 40 to 1 impedance match is something that's about the square root of 40 to 1, which is about 6.5 to 1. That is why whenever you do this kind of antenna, you will find an impedance matching transformer that is mounted right here at the end of the antenna inside a little waterproof box that will have a turns ratio of about 6.5 to 1. And that gives you an impedance match between your antenna, which is a very high impedance, and your cable, which is only 50 ohms. A very, very good practical application of impedance matching using a transformer. Now, Ray, I think you had asked, why do you decide when to use big wire or little wire?
Yeah, correct.
Okay, so let's do this. We're going to go back to my power pole. And up on the power line, we have a transformer that is, let's say, 12 kV versus on coming into my house, 120 volts. What would the approximate turns ratio be for that? Something to one. How many
Yeah.
times? How many times bigger is 12,000 to 120?
Yeah.
I hope it's more than 10.
Yeah. Yeah. Got me
That
on
would be a
that one.
100 to 1 turns ratio. Hi, Nate. So that would be 100 to 1 turns ratio to have 12 kV on this side and 120 volts on this side. Okay, so let us say that after wiring up an entire neighborhood, they discovered that this transformer was pulling, let's say, 10 amps. What would the current going out be? By conservation of energy, this is about 1,000 amps. Because it's still that 10 to 1 ratio, right? So where would you put the bigger, where would you put the bigger wire?
Would you put it in the right?
You would put it on the right. So this is the primary and this is the secondary.
Yeah.
So it would definitely be the secondary transformer in this case. And this would be a step down transformer. Now, the other thing you can do is, has anybody ever built anything with vacuum tubes? Don't be shy.
My dad when I was a kid.
Okay.
Yes.
What do you know about vacuum tubes? What kind of
They're vacuum.
voltages, what kind of voltages do they operate at?
It could be a linear, if it's a linear amplifier, it could be a couple of kV.
Yeah. So let's say that it's 3 kV and you want to make this from 120 volts. All right. So what's your turns ratio to get that? That would be about a 1 to 25 turns ratio. So basically, this is your primary coming on from your wall socket, and this is your secondary. Right? So it might turn out that at 3 kilovolts, you only need, let's say, 1 amp. How many amps would you need on the other side? You need about 25 amps. So in this particular case, where would your heavy gauge wire be?
Yeah, left side.
It would be on the primary side
Huh.
because you only need an amp. The current determines how big the wire has to be. Now, what does that also mean on the secondary side if you've got 3,000 volts?
Smaller wire.
Well, what it really means is that whatever wire you use had better be rated to handle 3,000
Rated
volts.
to handle it, yeah.
Yeah. Now, the current is no big deal. It could be very small wire, but the insulation on the wire has to be able to handle 3,000 volts, so you'll get arcing.
Right.
Which is why it's really important. Also, don't open it and stick your hand inside, because you'll end up frying yourself very, very easily. Okay, let's see. So we did transformers, current sizes, etc. Circuit components. Okay, we're on page 14 now. We're cruising right along. Resistors, capacitors, inductors, rectifiers, solid state diodes, transistors, vacuum tubes, and batteries. Okay, all kinds of good stuff. What is the following reason not to use a wire? Everybody should know this now. What is the following reason? What is the reason to not use a wire wound resistor in an RF circuit?
Because it acts like an inductor.
Because it acts like an inductor. That's excellent. Good. Okay. What's the advantage of a ceramic capacitor compared to other types?
Dissipates heat.
Actually, ceramic
voltage.
capacitors are really good at having a very high value
for
cheap
very,
to
very, very
produce.
small size.
Cheap to produce, they're not expensive.
And they're really cheap, yeah. Advantage for a, yeah, ceramic capacitors are really cheap. Modest capacitance for the size, but you know, a little ceramic disc capacitor is very, very cheap, and you can buy one for, you know, a penny. An electrolytic capacitor. So what you'll find is that in an electrolytic, you have a plus and a minus terminal, and they typically will have a very high capacitance. Essentially, a capacitor is two metal plates, right? An electrolytic capacitor is, if we were to look at it from the top, typically wound like this. So you have space in between the plates, and then you essentially have a gap, and the whole thing is wound like in a cylinder. And there's an electrolyte. Well, it's also polarized, the electrolyte. So you have a plus and a minus terminal. And let's say that you reverse those somehow, you'll end up going kapow. And that's why most electrolytic capacitors, when you buy them, if you notice, they will, in addition to having that on the top of the cylinder, they'll also have a mark that looks like that. Any idea what that is? It's not a plus sign. Mike, have you ever seen one of these blow up?
They vent out.
Electrolytics, yes.
Yeah.
There's
They make a,
sometimes have a vent on them.
yes, sometimes they have a vent. It's cheaper to make it like this, where these are score marks. And what happens is if you hook it up backwards, it'll break right there along these score marks, so that when you look at the capacitor, all of the stuff that comes flying out comes out in one particular direction. So when you accidentally hook it up backwards. So that's what an electrolytic capacitor does. Why is the polarity of an applied voltage important for a polarized capacitor like an electrolytic? Incorrect polarity can cause it to short circuit. Reverse voltages can destroy the dielectric. Capacitor could overheat and explode. It makes a loud bang when it goes. What's an advantage of using a ferrite core toroidal inductor? Okay, so if we are building a transformer for that end-fed half-wave antenna, and we go like this, here's a coil, and here's a coil. They have a different ratio of turns. Here's the core. So you can get a lot of inductance because all that material is, all the magnetic field is contained largely within the core. Now, it also turns out that different materials, which are made from different metals, there can be nickel, there's iron. Essentially, there are more of them too. You basically will grind them up into a powder, mix them with glue, and bake them into a nice cool shape, like a donut. So by selecting the materials that go into it, that determines the frequency response of the actual material. So if you're building an end-fed half-wave for one frequency, you wouldn't necessarily use the same exact material as for another one. There's, for instance, a type 43, and there's a mix 77, and there are literally dozens and dozens of different mixes of powdered metals that go into these things. And if you go to a company called Ferrite, it's a company that makes ferrites called Ferrite. They will actually publish the different sizes, shapes, and materials that they're made out of. You can very easily find that certain things are used for certain functions. For instance, I can grab as I unshare this. Everybody notice this? Anyone ever seen one of these on a power supply cord?
Oh, yeah.
Okay. This is actually not being used as a transformer. This is being used as an RF choke. Essentially, if there's any RF energy on this wire, what'll happen is that the material that's inside this little device, which is a little ferrite core, will absorb the energy, the RF energy, and burn it up as heat. Because your computer typically does not like RF energy getting into its circuitry. So essentially it functions as a filter. And by selecting a different material they decide what frequencies they want to try to choke off before they get into the power, before they get out of the power supply into your computer.
That's why they would be different sizes on different things.
That's why there are different sizes and different materials.
Okay.
And a ferrite core on display inputs to a computer from the monitor.
That's exactly right, because you don't want that getting into your monitor either. So, okay. What determines the performance of a ferrite core at different frequencies? That's known as the composition or mix of the ferrite. How does a ferrite beater core reduce common mode RF current on the shield of a cable? We just showed you exactly what that does. Basically, when you take a piece of cable and you put a ferrite around it, it's important to remember that every piece of wire that is carrying a current, what does it make? If there's a current flow, everyone hold up your right hand. Your thumb is the direction of the current. Take your fingers and roll them forward. That is the direction of the magnetic field that's generated. So in this case, a magnetic field will be generated this way. Well, a magnetic field likes to induce a current. Well, if I can put something here that reacts to a magnetic field by essentially saying, oh, you know, this mix, I'm going to absorb magnetic field energy. Essentially what it does is by taking the energy in the magnetic field and burning it up as heat, it destroys the current that's flowing through that wire. Sometimes you want that. If this is a piece of, let's say a piece of coaxial cable and you've got signal on the inside and then you've got signal flowing on the shield on the outside, well, typically you don't want the signal flowing on the outside of the shield because that gets into your station and causes interference. So by putting a ferrite core around that, you can actually choke that off, and that's known as a ferrite choke. Inductors are not perfect. Let's say you take an inductor and operate it above its self-resonant frequency. Okay, well, every inductor that looks like this also has some capacitance and some resistance, and it has a self-resonant frequency where, because it has, you know, properties like essentially the windings are a certain distance apart, that actually looks kind of like a capacitor. So every inductor will actually have a self-resonant frequency at which it will work best. And if you operate it and put it in a circuit where it's operating above its self-resonant frequency, it will actually start to become a capacitor and not an inductor. It will start to appear like a capacitor. Okay, here we go. Next, we're looking at diodes, semiconductors. Okay, so does anyone know what this is called? Right there. That would be a diode. Okay. A diode is largely made of silicon or germanium. And if I have this thing called intrinsic material, which I'll just call a little letter I, this can be like silicon or germanium. Silicon has a voltage to make it work of about 0.7 volts. Germanium is about 0.3 volts. Okay, so in order to make this material, which is an I, which is an intrinsic material, into this P stuff or N stuff, what we end up doing with it is we add some ions or materials which have a slight lack of electrons. They're actually known as holes. On the N side, we will add something that has a few extra electrons.
right? And that's known as our, so this becomes known as our N material. This is our P material. It's slightly different than neutral at that point. At which point then, if we put a positive voltage on the plus side and a negative voltage on the N side, that's greater than 0.7 volts, we will get current flow in that direction. This is known as a biasing voltage or a voltage drop. So basically, in order to get a silicon diode to work, you have to have a voltage differential of at least 0.7 of a volt. If it's a germanium diode, it has to be at least 0.3 of a volt. So that's for silicon. And this is for germanium, 0.3 volts. Okay. So we're going to draw now a sandwich. We're going to have a P and an N and a P. And we're going to take this N and we're going to tie it somewhere. Does anyone know what this is called?
Transistor.
That is a transistor. We've basically now taken a sandwich, 3 different layers of silicon, and turned them into a transistor. What happens in this case is that if we look at this as a diode, this part, what ends up happening is that if this is forward biased, so we have 0.7 volts needed to make it work, what ends up happening is that we can get an avalanche of current going this way. That basically everything jumps the first one. And if it made it past the first break point, it really wants to go that way. So we can get a much bigger signal. We can get a lot more current flowing this way than we ever could going down toward the bottom. So that would basically be how a transistor works. This is known as a bipolar junction transistor. Now, there's another kind of transistor which internally looks something like this. And what we end up with here is we have this channel. And what we do in this case is that instead of it being a current flow, what we end up with is a voltage differential between here and here. And when there is a voltage differential, it allows this channel to open up. So there's basically no current flow through here. It's just basically driven by somebody operating a gate. And in fact, this is known as the gate. This transistor is known as a FET, or field effect transistor. And these 2 terminals are known as the drain and the source. So basically the gate determines how much material flows between the drain and the source. This is an insulated terminal, and that's known as a field effect transistor. There are various different versions of this. There's something called a JFET, which is a junction FET. There's also something called a MOSFET. MOSFET transistors are actually kind of like the workhorse of the industry. They're used for very high power. FET transistors are also kind of like the basis of what goes on inside integrated circuits these days. Because they use almost no power to operate compared to a bipolar junction transistor. They're very efficient. Okay, let's see. The stable operating points for a bipolar transistor uses a switch and a logic circuit. Okay, is everybody ready for a nice graph? Okay, so this is what a transistor looks like. Okay, there's really 3 regions in a transistor. There's cutoff, and there's saturation. Okay, so a transistor, if you think about what it's designed to do, it is really trying to make a larger copy of a signal that's coming in. When you put a voltage in or a current in, a small current is supposed to make a really big thing out here. So what happens if you turn this completely off and you take the signal away? How much current goes through? And the answer is nothing. That's known as cutoff. That is its cutoff point, at which point it's not operating. Okay, but now what happens if you put so much in that this is now fully open? No matter how much more you put in, it doesn't make any difference. You're still getting as much through as you possibly can. That's known as saturation. Somewhere in that middle point, in that middle zone, is known as the linear range, where you basically have a linear relationship between the amount in and the amount out, and that is known as the linear range. Linear. Okay, so those are really three different modes of operation of a transistor. My handwriting is atrocious. Let's fix that. Okay, so that's the linear range. So if I were trying to operate a transistor as a simple switch where it's either on or off, I would use this range. This would be called off. And I would use this range. This would be called on. Those, I would just basically slam it on and off, the saturation and cutoff. If I were trying to make a copy of something, for instance, a radio signal, and make it sound nice and pretty, I would use this right here. And I would try to pick a spot where where an input, if I varied it slightly, would make a predictable corresponding change in the output. That would be known as the linear range. Okay. So now we're going to go back to about 1920. Anyone know what this thing would be called?
Vacuum tube.
A vacuum tube. Okay. Fundamentally, this works almost identically to a transistor, except that a transistor starts to work at 0.7 of a volt. This thing might not start to work until 300 volts. So it takes, it's a current switching device to make large copies of something. There is no reason you can't use a vacuum tube in its saturation and cutoff modes. Works just fine. People could make something called could make a computer with digital logic out of vacuum tubes. There's absolutely no reason you couldn't do that, except that it would be really big. So
require a lot of voltage.
And require a lot of voltage. Exactly right. So basically, you have three things. You have a grid, and you have a plate, and you have an anode. All right, this is your anode. This would be your cathode. I'll get rid of the word plate. Okay, so you basically have electrons being made down here that want to come up here to the anode. This is filled with nothing. So essentially what you have in here is a big area of vacuum. So this is basically, in theory, empty space, with the exception of all those electrons that you're then making available to here. Well, if you put a positive charge over here and a negative charge here, those electrons will decide that they want to occasionally get pulled through. Well, there's one way to stop this. You can, for instance, put a negative voltage right here and say, well, I'm already negative. Why would electrons want to go from negative to negative? And the answer is they wouldn't. By varying the voltage right here on this device, which is known as a control grid. For instance, if I were to put a positive here and make positives here, these things would be attracted to that point. And then once they got to there, they would be attracted even more over here, and you'd get a flood. So essentially, by changing the voltage on this control grid, you change the amount of you change the number of electrons that are permitted to flow from the cathode to the anode of the tube. So why would we do anything like this? Why would anybody use a vacuum tube today? Why would anybody use a vacuum tube instead of a semiconductor anymore?
Larger voltages.
Bigger
especially,
voltages, yeah.
For example, amps, the best power amps are apparently still tubes because of the power.
Yep, because since they're operating at such high voltage, what does Ohm's law say about power? Power is equal to I times E, right? Well, what does that mean? If you want more power, you can do one of two things. If you think about this, current is the number of electrons flowing. Voltage is the amount of oomph that each electron has.
Right.
So you can really do two things to raise your power. One of them, you can have more current, more electrons. The other one is you can take the same number of current, the same number of electrons, and you can boost up their voltage, their energy level really, really high. And that's why vacuum tubes are still useful, because there are certain things where you really want a lot of power. If you want a 100,000 watt amplifier, you can use semiconductors, but you'd need multiple modules. You could also use, 2 or 3 or 4 really big high voltage vacuum tubes and be able to do the same thing.
Like we used to see in TVs.
That's right.
Radar transmitters.
That's right. Radar system, 1 megawatt pulse radar.
Is that why we have to turn them off when the crews land on the cruisers?
Probably so.
We'll try them.
What is an advantage of the low internal resistance? Oh, wait, I missed one. The primary purpose of a screen grid in a vacuum tube. Okay, now you can have a vacuum tube that looks like this, again, which has a control grid. All right, this is the control grid running right through the center of it. Now, you can also have another one, which is called the screen grid. So you basically can have a screen grid to reduce the grid to plate capacitance. Essentially, by inserting another piece of metal in between, that reduces the amount of capacitance in between these two metal plates, because they're actually two physical metal plates. You can actually have, this would be known as a tetrode tube. If that screen grid wasn't there and you had 3 elements, what would that be called, everybody? What do you think?
That's the triode.
That would be called a triode.
And then there's the pentode.
And then you can have 2 screen grids. For instance, I could install a screen grid here, and I could put in another screen grid. And that would be a pentode. Notice we have 5 elements. 5 pentode. Okay.
Filament heater.
Sorry, you're a little quiet there.
Then you need a heater.
And then you need a heater. That's
You
right.
have to boil the electrons off from the cathode.
Unless you're using like thorium or something, right? I think you can
Hey,
actually.
Scott,
Yeah.
I have something on the wall that maybe many people haven't seen, and I'll show it very quickly.
Okay, let me unshare this so you have okay, go ahead.
Well, I gotta get over here to make sure I'm actually.
Oh, do you
showing
have
the
core?
picture.
Do you have core memory?
That is core memory,
Woohoo!
mid-1960s. It's the core memory out of an IBM 360 model 40.
Oh my God, Gene Amdahl.
But it's each of those little toroids was a bit. So you can turn them on, turn them off.
Isn't that basically like 1 kilobit per block?
I really don't know. It could be, but you had to stack 9 of these things up to get eight bits plus a check bit.
Right.
And I don't know, 1,000 years ago, I ended up getting a bunch of these and hung on to them for forever. And just this past year, I took one of them and put it on the wall just to say it's a nostalgic piece.
Okay,
of
I
art,
want
guess.
everybody to see this. Okay, so I'm gonna
University of
draw.
Southern California, Gene Randolph, Santa Barbara. Yeah.
Okay, does everybody see this right here?
Yes.
Okay, that thing that he just showed us is a core memory. It's a grid of cores. And what you would do with that is you would put a current through this one to do something, and there would be another one that would intersect it like this. If both of those turned on, you would basically have current flowing and it would set this core. It would actually magnetize the core and put a value into it. And then by running a current through, or by basically running kind of like a test current through and seeing if it was affected, you could see what the value of the core was, whether it was magnetized at that point.
Would those be ones and zeros for a binary?
Exactly.
On-off?
Yeah. And now here's the tricky thing. How do you reset it? And you reset it by running this, whoops. You reset it by running a current this way. Or one way or the other. So basically there was like a set and a reset. You had to be able to magnetize it and demagnetize it to reset
So
it.
that would interrupt the field.
That was in a
You basically
grid.
put half the current required to flip it horizontally and half the current to flip it vertically. And the sense wire will tell you whether or not that flipped.
Yep.
And that's how you figured out whether that was a 0 or a 1.
Yep.
Terribly expensive to manufacture.
Oh my God. Yeah. And maintain, and they weren't always that reliable. And
Yeah, a few of those things broke and you threw out the whole plane. That's how I ended up getting them.
Yep. Okay, let's see. What's an advantage of low internal resistance of a NiCad battery? NiCads can produce an enormous amount of current. They have very low internal resistance, so they can produce a huge, huge discharge. They were actually very popular for electric vehicles before there was something called a lithium-ion battery.
Scott, what was the question again?
The advantage of a NiCad battery.
Large current generation.
Huge amounts of very low internal resistance, so they can produce enormous amounts of current with very low heat. Minimum allowable discharge voltage for a 12-volt battery. If you ever take it below about 10.5 volts, you might have trouble charging it back up. So don't do that. Okay, let's see. We're on to page number 18. Analog and digital integrated circuits, memory, I/O devices, microwave ICs, display devices, and connectors. Okay. All right. There's something called an op-amp. All right. Now, an op-amp is basically an analog device that is an integrated circuit that measures a difference between a positive terminal and a negative terminal and gives you an output. That's what an op-amp is. The nice thing about it is that it's an analog circuit and it's contained on one chip. This can be a linear function. This can be a nonlinear function. It can basically slam full on or full off. That's called an op-amp. You can also use an op-amp to do something like this. You can take part of the output and feed it back into the input, into the negative terminal, and that can become a predictable, depending on the size of the resistor that you use, like this. That can become a very simple op-amp linear amplifier. So, and the gain of the amplifier is defined by the size of the resistors that you use, the values of the resistors that you use.
It's an idealized, very high gain amplifier. Really, really cool thing. Okay, MMIC. MMIC. That's known as a monolithic microwave integrated circuit. So the reason that there is something called an MMIC, which is a really important development, is because monolithic. What does monolithic mean? Completely self-contained. Microwave. We use microwaves all the time. I mean, they are the fundamental that makes this cell phone radio into something useful. And an integrated circuit, which means it's all on one chip. So essentially what this is an amplifier on a chip that operates at microwave frequencies. So that is known as an MMIC.
What was the definition again?
Monolithic microwave integrated circuit. And what's different about that is that it actually operates at very, very, very high frequencies. This could be like 3 gigahertz. And they can be used for transmitting. They can be used for receiving. They're kind of like a fundamental building block of microwaves. And when I say microwaves, I don't mean like microwave oven. I mean like microwave communications. They're incredibly important to microwave communications. Which of the following is an advantage of CMOS compared to TTL? Okay, CMOS. Okay, I'll share this again.
It's like a computer, it'll retain the memory.
That's exactly right. Well, CMOS and TTL. Okay. CMOS is complementary metal oxide substrate. It's the actual material on which a transistor is built. TTL is known as transistor logic. They both work. They both run between, let's say, 0 and 5 volts DC. 0 being off and 5 volts being on. Basically, this is for digital storage of things, right? Well, it turns out that CMOS is really, 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 really efficient. TTL, not so much. TTL burns up a lot of energy, turning the transistors on and off. CMOS typically uses FETs. FETs are very efficient. A CMOS chip is something like you would find inside your computer right now. That's how you can manage to get a computer that runs at 2.8 gigahertz and, does 100 million operations per second.
But it's also storing the information as to the functions that we brought up on the computer.
That's exactly right. So CMOS is how all that's done.
The BIOS chip.
Yep. Okay, what is meant by the term ROM? ROM is read-only memory. That's permanent storage of information. So a ROM is usually burned in with the program so that even if somebody turns the power off, then you turn it back on, you still have the information stored in your ROM. It's also known as non-volatile memory. So volatile memory is something that'll be erased when the power is removed. Those memory cores that Russ showed us, those memory cores are non-volatile mostly. They would typically, in fact, some of those that you showed us might actually still have some information in them all these years later, if they haven't encountered a magnetic field in the time. How is an LED biased when emitting light? An LED is a light emitting diode. We said that a diode typically has to have a voltage of about 0.7 of a volt in order to function. An LED is similar to that. The forward voltage might be a little bit different than that, but basically when an LED is forward biased in addition to allowing current to flow, the output function is that it emits light. That is a light emitting diode. This is very different from an LCD, which is a liquid crystal display. So there's an LED, which is a light emitting diode, and an LCD, which is a liquid crystal display. The way a liquid crystal display works is you basically have
a backlight behind this thing, and you have a grid where you have a point, and when you place a voltage at this particular point, it takes a crystalline material and puts an electric charge into it, which causes it to become polarized. When it does that, it polarizes the light coming in and the light coming out. And what happens is that you basically end up cross-polarizing your light, and you get a dark spot on your display. So backlighting is really popular for that because it makes it easier to see. But the thing about LCDs is that if I were to look at this, here's my crystal on my substrate, light comes in, gets polarized, gets repolarized coming out. If this particular spot was turned on, you'd basically get this dark spot on the display. If it's backlit, it makes it a lot easier to see.
Okay, that'd be the same thing as some of these fancy windows they've got that you can just flip a switch and you can't see through them. I mean, wouldn't that be the same?
Have you ever seen in Portland's airport, they have something where you put your hand on a piece of metal and it makes the entire display go black?
Right.
It's the exact same thing. That's a liquid crystal display.
Gotcha.
Pretty cool, actually.
Until the electricity goes off and you're using it in a bathroom.
That's right. Okay, which of the connector types is commonly used for signals, audio signals? Okay, so that would be something called an RCA plug. That RCA plug kind of looks like this. The old school audio plug from when we were all kids. Essentially, it's got a shell and a center pin, and it's not threaded. You just plug it in, and you'll typically find that these are red or white. For RL, I always thought that the red one was the right channel and the W was the white, which was the left channel. Sometimes you'll also see a yellow one, which is like for composite video. Oh, just like that. Thank you, Ray. He's got a red one, and he's got a red one and a white one.
There you go. Yeah, I don't have a yellow one at the moment. So
well, they also had ones that were red, green, and blue for composite video or for RGB video. So those are known as RCA plugs. They're usually used for audio. Okay, let's see. Connectors. All right, so what I'm going to do is I'm going to clear this out, and I'm going to unshare, and I'm going to go to Pasternak Enterprises. The reason I'm going to go to Pasternak is because they sell everything. And okay, let me share this. And see, the great thing about being able to do a class online is that you can just go to the web and share cool stuff. Okay, so Pasternak Enterprises. Okay, so here we go, right there.
Oh, SMS.
Oh,
it's SMS.
Oh, so let's see. How about PL 259? Let's see what they've got for PL 259s. Okay, so PL 259s. These are known as UHF connectors. Notice this bulkhead UHF. There's something called a mini UHF, which looks a lot like an SMA. Right here, this is the one that's highlighted. That's a PL 259 to SO 239 potentially. Here's another one, UHF male, or sorry, UHF female. All right, so part of the tricky thing with UHF connectors is that they're terrible for use at UHF. UHF means universal high frequency. And it came about a long time ago before people were using a lot of UHF. So the PL 259 and SO 239 connectors are known as UHF connectors, but they're really only used for HF and a little bit of VHF. For connectors that are used for higher frequencies, we would use something called like an N female or N male. Let's see what this comes up with.
We'll go to N connector. There we go. That's an N connector. And there's a male N connector, and notice it's got separate shells. It's got a center pin. Those are, in addition to being excellent for use up to like 3 or 4 gigahertz. Well, they actually say 10 gigahertz in this case. In addition to that, they're also water resistant, if not waterproof, if the gasketing inside is done correctly. So that's known as an N connector. There's also something that is used frequently now, which is known as an SMA. And that is a little SMA connector. Notice it's teeny tiny. That's actually what you'll find on most handhelds these days. For instance, if I go to my handheld radio and I pull this up and I unscrew this, you will see in here that is a male SMA connector. Inside the radio, you will see a female SMA connector. If I pull up a different handheld, sometimes the polarities will be different. You'll have a female antenna connector and a male radio connector.
The SDRs are using SMAs too.
Exactly. And it's because they're really good up to the gigahertz range, and they're fairly inexpensive, and they are easy to use. So that's known as an SMA connector. Okay, practical circuits. We are now on page 20. Okay, so we have now gotten into practical circuits. So we're talking about power supplies. All right, so what we're going to do is, the first thing I'm going to do is draw this wave. Okay, how many degrees are in this wave from 0 degrees up to the end?
360.
360 degrees. Okay, so if I were to say, for how many degrees is the voltage positive and how many degrees is it negative?
180.
Right, so the first 180 is positive and the second 180 is negative. So if I were to use this waveform and say I'm going to build a circuit that basically only uses the voltage when it's positive, and I'm going to call that DC, and use just this and then flatten it out and then use this, how many degrees of that waveform would I be using to make my voltage?
Oh,
I'd be using 180 degrees of my waveform. Now, if I were to instead build a circuit that used this and took the negative part and managed to flip it over, how many degrees of my wave would I be using?
360.
All 360. Okay,
Yeah.
so the red, this would be known as half wave rectification. And the green would be full wave rectification. Okay, so which is a more efficient way to build a power supply?
Full wave.
Full wave, because I don't waste some of my power. Okay, the advantage of a half wave rectifier is that it's really, really simple. A half wave rectifier circuit basically looks like this. That's it. That's a half wave rectifier. That's the basis of a half wave rectifying power supply. Because when the voltage goes negative, it tries to go backwards and it can't do it. So that's it. That's a half wave rectifying circuit. To make a full wave rectifying circuit, you need to be a little more tricky. You basically need something that would intentionally flip itself. So here's coming in, and I always have a little trouble drawing this. Let's see, in, out, and it goes like that. So the path is, it goes like this, and like that. And then the other half of the time it comes like this, and it goes like that.
Yep.
Did I get that right?
Yep.
Oh, good. Okay.
So what, okay, so let's count the diodes, everybody. How many diodes are needed in a half wave rectifier?
4 of them.
In a half wave?
Oh, 2. No, 1.
Just one. That's right. How many diodes are needed in a full wave rectifier?
That's gonna be 4.
You got 4. All right. Very often you'll be able to find these in a bridge, like like an integrated circuit that has all of those diodes built into it. So sometimes it's actually easier to build a full wave rectifying power supply because you can actually go and buy a high current device to handle that.
You get the most power from that versus the other one.
Okay. So what is the output waveform of an unfiltered full wave rectifier? We kind of drew that. You basically have something that looks like this coming out of the half wave rectifier. Out of the full wave rectifier signal, you'd get this. So you basically have pulses coming out at twice the frequency when you're talking about a full wave rectified power supply before you unfilter it, before you filter it. Right. Okay. Now, what do you do with that ugliness? You have to make, I mean, well, what is it? What's the function of a power supply? What do we use a power supply for?
Power things up.
We want AC going in. And what do we want coming out?
DC.
We want DC. Are there any bumps and ripples and noise in DC? Ideally.
No.
We have 13.8 volts DC. It should have very little ripple. Well, we also have 120 volts AC coming in. And we know, because it's AC, that we have 170 volts peak and negative 170 volts peak here. Right? Well, that's a lot of noise. If we first start to clean this up, we get this. Right? We full wave rectify it. We get a train of pulses that go all the way up to 170 volts. Right? So, okay, well, we're not going to want to do that to start. What we're going to do first is we're going to make it so that 170 volts is a considerably lower voltage. So we're going to take it and we're going to run it through a transformer. So now we're going to make it so that instead of 170 volts peak and 120 volts AC, we get something like 20 volts AC. And with a peak of 28 volts and negative 28 volts. Okay. So, okay, we're getting closer to something we can work with. And that we did that through the use of a transformer. Well, now we have the waveform that looks like this, which is basically a bunch of bumps. And we're going to take this and we're going to put a filter across it. And the way that we do this is we now have this diode, and now we're going to take this and put it across a capacitor. Capacitors charge up and then discharge, and charge up and discharge, and charge up and discharge. So what'll happen here is that when we get to the peak, the capacitor will charge, and then as the supply voltage goes down, we'll start to discharge, but the capacitor will catch it. So now we look like something like this. Right. Well, that's better. Does everyone agree that's better than what we started with?
Yep.
Okay. It's still a little bit noisy though, right? So maybe we want to add a bigger capacitor, but yeah, we still have a problem. So now what we're going to say is we want our voltage to be capped at like this level. We don't really want all that extra stuff above. So we use something called a Zener diode, which is a reverse diode. Essentially, it's a reverse diode with a voltage reference. Normally, we think about diodes as flowing in the forward direction, like that. A Zener diode, it turns out, you actually set it up that it would work in the forward direction. And normally diodes don't work in the reverse direction, but in this case, if you put a high enough voltage across it, it says, okay, well, I'm going to make a reference voltage. My reference voltage in this case is, let's say, 13.8 volts. All right. Or let's say it's 12 volts or something. That's my reference voltage for my diode. And then you're going to have a voltage, maybe a voltage adjustment or a little current adjustment or current limiting. And what that will do is basically take this output and clip off all the noisy stuff on top. So essentially now the voltage that you have coming out is really a nice clean 13.8 volts DC. And that's essentially it, because we've now full wave rectified it instead of half wave. Our capacitor doesn't have to work as hard. And now we have a now we have an actual voltage that comes out. Now, the other thing you can do with this to make it able to handle more current is then you can put a transistor across the output that will deliver more current. That's known as a pass transistor. You can have multiple pass transistors. That's how you would develop, let's say, a power supply that was 12 volts at 50 amps. You might have 6 big transistors that are delivering power to the load.
This is a crazy question, Scott, on the power supplies. I mean, this is maybe a little off track, but
No such thing.
I use them for lighting in the garage. I've discovered that when I grab them, some of them will cause the LEDs to strobe, and others will not.
Weird.
Means that it's not filtered correctly.
That would be my guess.
Okay.
I have also noticed that if you ever done this, if you have like a fluorescent light and you have an amplified speaker, if you take the amplified speaker, which normally plugs into, let's say, a device, right? Through an audio cord, you unplug it. You plug it into the device and it sounds fine. You unplug it and it goes,
right.
It's picking up 60 hertz from somewhere or 120 hertz.
Okay.
That'd be my guess.
Yeah, it's weird when that does that. So a lot of them I look for the, when I'm looking at them, they'll say that they're switched. 12 volts.
Well, and that's the thing. A switching power supply is something totally different.
Okay.
What we just drew was a linear supply. A switching power supply, which is actually the very next thing that's mentioned, is kind of like a multi-stage thing. Okay. So let's say that we made our 12 volts, right? Or let's say we made any voltage for that matter. That's kind of DC-ish, right? So here's our voltage coming out and it's at, let's say it's at 140 volts or any voltage for that matter. Actually, it wouldn't be AC. It would be just like 140 volts. We then take that and we use a transistor operating at a very, very high frequency to switch the output on and off, which looks like this, right? Okay. We now take a transistor and we use it to switch that voltage on and off very, very fast, possibly in the range of 20,000 times per second. All right. So now what we've done is we've created something that is a square wave operating at 20 kilohertz. All right. So now can we then, because it's a square wave, but it's still AC, right? Can we put that through a transformer?
All right.
Can we do that?
Yeah.
Yeah, we can. And in fact, because it's at 20 kilohertz, we can actually have a much smaller transformer, because what did we learn about inductors? XL is equal to 2 pi. What's that letter now?
Yeah.
FL. If we raise our frequency, what happens to our reactance? Our reactance goes up, which basically means in order to do the same effective job, we can get away with a much smaller thing, physically smaller. So this is basically the core of what's known as a switch mode power supply. Now, the act of taking that
DC and switching it on and off, what do you think that makes? Ray, what do you think that generates?
You lost me on that one there. My train of
Well,
thought
I
was-
mean, if you've got a frequency now that you've made of 20 kilohertz,
20 kilohertz noise.
you get noise,
yeah, noise.
right?
Okay.
And you get it not at that, not just at that frequency, but you get it at harmonics. Like a lot of harmonics, because you have a square wave. And when you have a square wave is actually made of a sine wave plus another sine wave plus another sine wave and another sine wave. And you can show that basically a Fourier analysis of a square wave is full of like an infinite number of harmonics of the fundamental. So you have to filter the heck out of it to make sure that you get a real sine wave out. Which is why because basically what this is known as an inverter. It's now
Okay.
creating AC from DC, or now then you have to try to make DC back out of it. So the dirtier it is, the worse off you are. So
Yeah, that's where my transformer or my power supply I originally had hummed like crazy. Yeah, I understand that now.
yeah. So I mean, some of it might be actually some of it that you could physically hear, like
Yeah, that's
that.
what it had.
Okay, that's different. Typically what that is the fact that you have the power supply itself internally having a transformer, and the transformer, in order to reduce eddy currents,
Oh yeah.
is made of individual plates that are then sandwiched together and glued, sandwiched and glued together.
Right.
And if any of them come loose, they'll actually physically rattle and make a humming sound.
You heard that humming sound when I was talking to you once before originally.
Yeah.
When I
Oh yeah.
Okay. Because I looked for it thinking capacitor or something might be bad. So
Yeah.
okay,
It can be the transformer itself, because
Oh,
you
look
don't
at
want to
that.
make a transformer out of a solid block of metal,
Right.
because then you get eddy currents swimming around inside the metal that burn up energy. So you make them out of individual laminar plates, like a
And they-
laminated transformer.
You know, they separated and they're basically vibrating.
Yeah, they can vibrate if they're not glued together really tight. They're trying to push apart from each other.
Right. Okay, makes sense. Now I know what to look for when I go to try and get into it.
Yeah.
Hey, Scott, when
Yeah.
when you're dealing with power supplies for amateur radio, like 3.8, 13.8 volts,
Yep.
I was wondering why they're so darn expensive. And maybe it's just this, that you're fine tuning the the wave and making sure it's coming out very clean and taking
Well,
the noise out.
let me ask, when you say expensive, define expensive. And what
They're all around they're all around $150.
that's cheap, if you ask
Yeah.
me.
10-4.
Yeah, well, I mean, because I work in factory automation, and a 24 volt, 20 amp power supply is $200 something. So if you can get a power supply that's 13.8 volts and stable, that operates, and let's say it's a 35 amp supply for $120, that's actually cheap.
That's a deal, yeah.
That's
Okay,
actually
I'm
cheap.
comparing it to a $400 handheld,
Yeah.
2 meter,
Well-
70 centimeter.
Well, let me ask this question. That's like a switch mode power supply. Why would a 13.8 volt Astron linear power supply that's rated for 35 amps be $300 now?
No idea. Shortage of parts.
Yeah, shortage of parts. It's a lot of
Okay.
metal, a lot of steel, a lot of iron.
Because they're heavy.
They're heavy. That's right.
That's what that one is that I've got that hums.
Yeah. And that's actually not surprising. I mean, that's, a linear power supply has a big transformer with a big iron core. So, okay, let's see. Do we have to go through the schematic diagram? I can just draw up there what they are. Okay, here we go. Let's see, a field effect transistor. This would be a field effect transistor. Right? That's known as a field effect transistor. This is a bipolar transistor. So this is a FET. This is a BJT, a bipolar junction transistor. And in fact, this is an NPN. And the way to know what's an NPN is that the arrow is not pointing in. NPN. Okay, that's an NPN junction transistor. A diode looks like this. A Zener diode is a special looking diode which looks like this. So this is just a plain old diode, and this is a Zener diode. Okay, let's see what they call a solid core a solid core transformer. Okay, I would just call it a transformer. This is a transformer. They can also draw it like this. That's a transformer. Okay, a tapped inductor. This is an inductor. Right? This makes it a tapped inductor. In other words, you've actually soldered something to that and you're pulling a signal off halfway through. So that would be known as a tapped inductor.
Now, when Scott?
Yeah.
When would you use a tapped inductor? I've been listening in, and some of this is going over my head. I'm not going to lie, but it's fine because I want to review the videos and I'm going to continue going over the notes. But some things I'm trying to figure out the practicalities, like the practical use.
Yep.
When would
Here
you
we
use
go.
a tapped?
I will show you a perfect example of a tapped inductor. Okay.
That'd be kind of like the same thing as like, what is it? There's a coil that you can, use in transmitting that you just take an alligator clip and
Exactly
just
right.
change it. You can
That's
just use
exactly what I'm drawing. Okay.
Oh, okay.
So let's say that you have an in that goes into and goes out of. All right. This is known as a T network because it's in the shape of a letter T. This would typically be a variable capacitor, and so would the other one. All right, so a variable inductor, you want to be able to change the value of the inductor. One way to do that is you basically have a very expensive roller with a core, and you have a device that sits on the coil as it spins, and this end is shorted so that you basically have, and this end goes to somewhere, and then you basically have this value right here. And that gives you, as this thing turns and rotates, this thing is on a mechanism that allows you to slide back and forth. And it also has to be silver plated because it's got to be a good electrical contact. A roller inductor is a very expensive thing, right? They work great. They're continuously variable, but they're really expensive. A cheaper way to do that would be to have this.
Multiple tap points.
Have that go to a switch.
Switch.
Where you have a switch that you can select to different values, and that gives you an output, which then would allow you to instead break this point right here and connect that up here.
Right.
Which allows you to change the value of the inductor that you're using by just switching different positions in, different taps.
Okay, I haven't seen one of those yet.
Here,
Yeah, that's fine.
here, I can show you a picture of one. MF.
Thank you.
Was
I know
it
the
Wolf?
radio club here has a whole bunch of different antennas, and I know Chris here, his whole backyard, he has like antennas all over the place. He has the T antennas, he has like antenna towers, he has all these horizontal and vertical antennas. So I've been able to see a couple different antennas, and he's explained to me which ones work and why. But I don't think I've seen something like this. That's why
Here,
it caught me
right
off
there. Right there, you notice there's your coil and it's got all those single wires coming off of it. Those all go to a switch. By selecting the switch position, you basically select the wire that's connected to that part of the coil.
Kind of like
See,
a
that's
switch, taking an alligator clip and stabbing it on where you want
It's just like taking an alligator clip. and sticking it on where you want, except that this is a permanent location and you don't have to open the case.
Yeah, that's Wolf River coils, I think.
Yep.
That sell them.
Okay, we're on to digital circuits. Digital circuits. Okay. So digital is really easy compared to analog. And we're gonna take lunch at noon, by the way. We'll take a short lunch because this is a short day. Okay, which of the following describes an AND gate? Okay, so when we're talking about logic, we're talking about zeros and ones. There are only zeros and ones. And you know there are only two kinds of people in the world, right?
Those that understand binary and those that don't.
That's right.
Zeros and heroes.
That's right. Okay, zeros and ones. All right. So which of the following describes a two input AND? Okay, so if I were to draw this and we have two different things, we have, let's say we're talking about Ray and myself, all right? And Ray either calls up a 0 or a 1, and let's say we raise our hand with or without any fingers. Okay, we're doing an AND. We're looking for a condition where both Ray and I have raised our hand with a single finger. Ready? Go ahead, Ray. 1, 2, 3. Okay. So Scott put up a 0 and Ray put up a 1. So this would be Scott and this would be Ray. So a 0 and a 1. Okay. So the end result is a 0 because we both put up, we didn't both put up a finger. Okay. Ready? 1, 2, 3. Okay. So Scott put up a 0 and Ray put up a 1. All right. Ready? 1, 2, 3. We got the same thing. Okay. Well, you get the idea. If we both put up a 0, it was also a no. If we both put up a 1, that would be one of those rare instances when we both said yes. This would be known as an AND gate, where the output of the thing goes high when this is 1 and this is 1. That makes the output true. All right. Now we could also do something called a NOR gate. We could also do an OR. So let's do an OR. So we would take a look at this truth table here and erase those conditions. And we would say, if either Scott or Ray put up a finger, the answer is yes. So yes, 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 and not there. So basically an OR would be if either or. Now, there's also something called an XOR, which is exclusively one or the other, which is if we both did it, then no, only one can be true. Then there's also something called a NOR, which is neither this nor that. Or you could take that as an OR and invert it. So that would be something totally different, which looked like this. We just invert it. And the great thing about digital logic is that there's only two possible things it can be. It can either be true or it can be false. And because of that, it's really easy to work with. So for instance, when they say output is low when either, okay, so they ask for a NOR gate. Okay, so this is a NOR gate that I just drew right there. So the output is low when either or both inputs are high. See, that's confusing to me. What it really means is the output is high when both of the inputs are false. That's the other way to say it. You can either say that if both of the inputs are false, then the output is true, or if anything is true, then the output is false. And true equals high voltage, and false is equal to low voltage, or on for high or off for low. So this is really how a lot of people, if you think about it, you know, they conduct their day, they conduct their life. If this is true and this is true, then I'll go and do this. Logic circuits just basically automate that for you based on how you've programmed it. Okay, so a 3-bit binary counter. So this is why binary is so cool. Binary being 0 or 1. So let's say we have 3 bits. We have bit 0, bit 1, and bit 2. How many different things can we represent with that? Well, we can go 0, 0, 0. That's everything false. We can go 1, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1, 1. We have 8 different things that we can represent with just 3 bits of information. So a 3-bit binary counter can represent 8 different values. So what is the relationship between 3 bits? 2 to the 3rd power is 8. So how about if we had 10 bits? How many different things could we represent? 2 to the 10th power, which is 1024. If we just doubled that and we had 20 bits, we could go to 1,000,000. We could represent 1,000,000 different things. The reason for doing this is because, for instance, let's say that we are trying to measure the value of a signal at a certain point in time. And we want to record that for posterity. Well, let's say that we had 3 bits available to us. What values could I represent with 3 bits? I could represent 0, 1, 2, 3, 4, 5, 6, and 7. Okay, well, what if this is 6.3892? What would I record that as? If my whole alphabet is only 0 through 7, what would I probably record that value as?
6.
I'd record it as 6. Okay. If this was 6.01124, what would I record that as?
6.
6. Okay. And if I tried to recreate it, what would happen? All I would know was that it was 6, right? This is actually known as quantization error. This is known as audio or analog to digital conversion, A to D conversion. So if anybody has ever seen like a CD player or something, and it said it was a 10-bit A to D converter, or something that was 14-bit or 16-bit or 18-bit, what that means is you have more resolution and your quantization error gets smaller, which means that when you go to replicate something, you can do a better job of it because you had more information available to you, because you were more accurate when you recorded it. So anyway. Okay, a shift register. A shift register is something that says if I have a value of 0, 1, 1, 0, 1, 1, 0, a shift register would take this value and say, let's say that I did a shift right. Everybody dance to the right. Okay. So I have things that come in from the outside world. I would end up with this goes here, 1, 1, 0, 1, 1, 0, and then a new value of 0 comes in where it took its place. What happens to that 0 that I just moved out of the way? I might use it for something. I might also just throw it out. Right? If I then shifted it again, I'd have a 1 that came flying out of here. And I'd now have another 0 thrown in there. Make sure I get that right. And either I use the information or I get rid of it. That's known as a shift register. It allows me to sequentially use information.
Is that where you get an incremental increase as you do a logic loop?
Say that again.
Is this where you get like an incremental count going in a logic loop by doing a shift register at the next record?
I'd say, yeah. I mean, basically you're just looking at whatever's there. It's kind of like you can actually use a shift register as the basis for something called a FIFO or LILO, or basically moving things into a stack of information, being able to take information back out. So for instance, if I had a value that was coming in over here and I wanted to use it, and I wanted it to be the first one that I used, I could shift everything left. And then when I wanted to use it, I could shift it back to the right. So the way that I drew it the first way, that would be called a FIFO, or first in, first out. So that the information that came in first would be the first thing to go. Then there's also something called a LIFO, which is a last in, first out, which would basically be moving something from one side and then using it first.
Is this the baud rate pushing the digital?
No, this is actually for like memory storage.
Oh, okay.
You know, how to use information. All right, let's see. We've got a few more minutes and that'll get us to a good point. Okay. All right, so oscillators. So an oscillator is something that makes a signal at a specified frequency. So essentially everybody's heard oscillation. If you've ever heard a PA system go, that's an oscillation. Essentially part of the output is then being fed back into the input and being amplified. So an oscillator is a filter and an amplifier operating in a feedback loop. In this case, it would be a positive feedback loop. Now, by specifying the frequency that's coming through by using the filter, that determines what frequency the oscillator oscillates at. If you're just, hearing like, a PA system that's going into oscillation, part of the problem is that you have no prediction of what that frequency is. An LC circuit. Okay, anyone have any guess what's in an LC circuit? Two components.
Inductor, capacitor.
Yep, inductor and capacitor. Okay, so we have determined early on this morning, everybody remember that a capacitor, if I were to draw its reactance and impedance, comes down this way. An inductor, on the other hand, comes up this way. If I pick them so that their frequencies so that their impedances are exactly equal and opposite, what will happen when I add them together? They will null out and I will get nothing. So if I were to pick those values, that I have 2 pi FL for this one and -1/2 pi FC, and I'd make them equal to each other, I get 2 pi FL equals 1/2 pi FC. And I would end up with this equation. F equals 1/2 pi square root of LC. This is a really important equation because this is the resonant frequency of an LC circuit. This right here is super, super important for tuned circuits. If I were to make a circuit that looked like this one on the left, my resistance would go like this, or my impedance would look like that over a range of frequencies. I would bottom out at the resonant frequency, which means that if I have a signal that I'm trying to push through, what would happen when I was at the resonant frequency?
Maximum power, maximum.
I would get maximum power through. So that means that at my resonant frequency, I get maximum power through, and it drops off as I get away from that frequency. So if I were to draw the passband of this thing, which is a filter, and it looked like this, I would look at my half power frequencies, and this would be my bandwidth of my filter. Now, if it was a really sharp filter like the one we just drew, that it looks like this, my half power frequency would be right here, and my bandwidth of my filter would be really, really narrow. Sometimes I want that, and sometimes I don't want that. That's why we have the ability to pick resistors and things like that and put them in a circuit to reduce what's known as the Q of a circuit, which is the peakiness. So what determines the frequency of an LC oscillator? By this equation down here. The frequency of an LC oscillator in a tank circuit is the values of the inductance and the capacitance right there, the LC. Which of the following devices describes a linear amplifier? That would be an amplifier in which the output preserves the input waveform. If we were to draw our response of our transistor, it would look like that. Again, here's the linear region. We would want to use that in the linear region so that the output was proportional to the input. A class C amplifier is very efficient. So the classes of amplification, if we just use this would be class A. If we were to go from here to here, for instance, this might be a class B. If we were to go from here to here, that could be a class C if we were to use like the entire thing. Well, obviously that's not very linear, but it's really efficient. FM, because on our receiver, we cap the waveform anyway, we eliminate all the noise. FM is great for class C. How do you determine the efficiency of an amplifier? Efficiency of anything is power out divided by power in. If I have 50 watts out and 100 watts in, my efficiency is 50%. Where does the other 50 watts go? What did I hear? Heat. That's right. That's right. So you better have a heat sink to get rid of the extra heat. What's the reason for neutralizing the final amplifier stage of a transmitter? Well, okay, let's draw this. This is a transistor. What do you see right there?
Plate.
What is this thing?
Plate.
Well, this is actually a little transistor. But yes, this is a plate. And what's this over here? The other part of the transistor. This is a field effect transistor. What is that thing? That's actually capacitance.
Oh.
And this is connected to an inductive circuit and such. And so you may actually find that if you don't neutralize your transmitter, your output stage of your transmitter, that you actually have some combination of inductance and capacitance. And what happens if you have inductance and capacitance? What does that make?
Filter.
It can make a filter. What else? It has a resonant frequency. If you're
Oscillator.
transmitting and part of your something comes out and then back in, what do you then have?
An oscillator.
You have an oscillator. That's right. And what frequency is it oscillating at? The answer is, I don't know. I had that happen once. I had an amplifier that went into self-oscillation at some god-awful frequency. And I actually had to like take it out of service and figure out what was wrong with it. It had to be neutralized. So that's called neutralization. Okay. Well, we are on 26. Everybody ready to take a 20-minute lunch? Is that good for everyone? All right. My voice needs a break.
So does my brain.
Yeah. Everybody good so far?
Yeah.
Okay. All right.
Taking it in, trying to understand it.
Well, there's, but a lot of it is stuff that you've already seen. It just didn't have a name.
Yeah. What you read in the book is now having a name and a look.
That's right.
Yeah.
All right. We'll see you all in 20 minutes.
Okay.
All right, let's see. Anybody with any questions while I finish eating my lunch? Hey, Russ, where exactly are you? You're still muted, Russ. There we
Yeah, I
go.
think I'm off mute now. I'm in Portland, Oregon.
Okay, what, in Portland proper or suburb? Or?
Actually, west side Beaverton, more specifically, Claremont
Okay.
subdivision. Or where are you?
I'm in Eugene,
Okay.
south side. South side of Eugene.
Okay.
And I have to say, given the fact that it's pouring down rain, it's not a bad day to be doing this.
That's true. It isn't raining a great deal right where we are, but I know it has been off and on.
Yeah, set condition, Oregon.
Yeah, I've come to understand that. It's funny because I was like, every time you make a plan to go out, there's gonna be a rain forecast.
Right.
I charged up my electric skateboard and I was like, after class today, I'm gonna just take 30-45 minutes and go electric skateboarding outside and just spend some time. And it's been raining all morning.
Yep.
Oregon means you never see a celestial event.
Oh, he's out on the coast too. So
little did you realize you might electrocute yourself, right?
Oh, it's low voltage.
Yeah.
But
okay.
The interesting thing about that is that, you know, people who come to Oregon for the very first time in the summer think it's really nice all the time.
Yeah.
I fell victim to that.
Vicious rumor.
Vicious rumor.
I visited Oregon in July. I said, oh my God, it's so nice here. And it didn't rain. It was always dry and cool. And
Oregon, where we respect the water cycle.
Yeah. No, exactly. I had, you know, there's 3 months of dry, and I came in the dry and thought, man, what a
You
great
did
place.
say you wanted it green, right?
I know. Well, you know, otherwise
California brown, we green.
Otherwise, it turns into Eastern Oregon or Arizona. So,
well, speaking of Arizona, after 50 years of living there off and on, my wife and I decided to move to Portland last fall.
Okay.
Because our family, our granddaughter, and I mean, our daughter and her family and the granddaughters and everything live here. You know, we had come up at various times of the year for 20 years, but when we hit here at the end of October, November and December, very heavy rain.
Right.
I think February and March were very heavy rain. I can't remember, but half a dozen people threw a going away dinner for us in Scottsdale. And they gave us a present, which was this stick it on a pole weather station out back. Well, now when I talk to them in video, you know, Zoom, almost every week, I can tell them that, you know, how much rain we've had. You know, this month we're now over 3 inches.
Mm-hmm.
April was, you know, not too bad.
They must be envious.
Well, you get a lot of crap from people locally about being reverse snowbirds.
Just show them the moss between your toes.
Yeah. You know, I have moss growing on my car. That's how I know. That's how I know it's time to wash it.
You aren't in direct sunshine. You know what to expect.
Oh, wash your car.
I know. Well, that's how I know it's time to wash it.
That on the pollen count that's falling on your hood.
Yeah, it turns my car green.
No, we get yellow up here from the pine trees.
Yeah, well, I think of it greenish yellow. Yeah, it get, and there was like I want to say like a 2-week period when it didn't rain, when all the trees were going crazy, and I mean it was like, you know, like paste.
Every once in a while, the Coast Guard has to declare small craft warnings on I-5.
Hey, Scott.
Yeah.
You were talking about Echolink earlier. Do you do any 2-meter nets up there that are on Echolink?
You know, not per se, but I use Echolink when like to get into my club repeater when I'm traveling. And it's actually really nice. I mean, the only drawback is that it takes about a second for the transmitter to key up. So they have to basically be, waiting for Echolink stations to come in, but it's not bad. It's great to be able to do it. And I travel for work way too much now, so
I got into using DMR.
I got it.
I volunteer for search and rescue, and we use DMR quite a bit for that purpose. But traveling for work, I mean, it's easy. I can take my little open spot with me and my little handheld and access all sorts of stuff. So DMR is kind of, cheating when it comes to ham radio, I feel like, but it's super convenient.
It's
I don't
hybrid.
understand the first thing about DMR yet.
It's if you have any type of IT background, it's the same as VoIP. It's voice over IP, but for radio, right? Like it converts the radio signal to an IP based that computers communicate. You can send that across the internet, and when it gets to the other side, you can turn it back into radio form, and that's the simple form of it.
Well, so do you do do you do Arden too?
I do not.
Okay, because we actually have a very strong, a very strong group of people with IT backgrounds here in Eugene, and actually out to the coast and up to Salem, up to Portland, Corvallis, and yeah, they're actually at the point of modifying telephone systems so that they work over the Arden mesh network.
That's pretty cool.
Yeah. So you basically have a phone number that you dial to get into a certain area, and then you basically dial into somebody's bat phone and it rings on their desk, and
nice.
It's basically a radio replacement for all of the cables.
Scott, on the bandwidth maps you had, or the schematics, they keep showing phone. Does that mean literally transmission per se? Like, I kept expecting, voice transmission or something, but instead it says phone, data, carrier. So I'm assuming phone means literally mic transmission.
Phone is voice.
Okay.
Like telephony. All right, you guys ready to go? Okay, I don't hear anyone saying no.
Hey, Scott, quick question for you, please, sir.
Yeah.
Will this video be available later to review?
Yep.
Great.
That's the plan.
Thank you. Y'all being recorded as we speak.
Yep. Okay, here we go. We are on what I see as page 26, which is receivers, transmitters, filters, and oscillators. Okay, the frequency above which a low pass filter's output power is less than half of the input power. All right, so that is again known as the cutoff frequency or half power point. There we go. So if I have a filter, this is a good opportunity to do this. So we're going to draw our little why can't I draw straight? There we go. We're going to draw some little frequency maps. And okay, so different kinds of filters. If I have a pass band that is low, that's known as a low pass filter. If I have a pass band that's high and goes out to infinity, that's called a high pass filter. If I have a filter that looks like this, that's called a band pass filter. And something that looks like this, that's called a notch filter or a band reject. So those are basically our four different kinds of filters. Now, in actuality, again, a filter does not look like that. It looks like that. Every filter has something that looks like this and this, and the pattern actually might, look something like that. And in some cases, there's a little bit of overshoot and then a little bit of like this. So when you get into the mathematics of building filters, you'll see names like Chebyshev.
and there's a whole bunch of others.
There's a
Many of them.
wonderful radio company called Collins Radio also.
Yeah.
Beautiful filters.
Well, again, those are mechanical filters probably as
Yes,
well.
a lot of them were mechanical filters.
Mm-hmm. So all the filters have different cutoff frequencies based on what they are, but they also have different patterns. Some might have a little bit of ripple toward a little bit of overshoot. Some might come out like this, and a lot of it's dependent on the mathematics that are used. So one of the most famous filter designers, his name was Chebyshev, and this is actually something that you'll typically get to on the extra class exam. I don't even know if they're really covering it a whole lot anymore, because there's a lot of digital filtering that's done. But there's like a Hamming filter, Hanning. There's a few others that basically the most important point about filtering is that when you get to right here, this is the half power point, and this is known as the filter bandwidth right here. Okay. What would the impedance of a low pass filter as compared to the impedance of a transmission line to which it's inserted? Okay, so if you have a 50 ohm coaxial cable, typically would install a 50 ohm impedance into it, a 50 ohm impedance filter. Let's see, filter's maximum ability to reject signals outside its passband. Okay, so if I were to draw another filter that looked like this, here's a bandpass filter. Ideally, there's a nice little square wave, right? Filters don't work like that. Filters might do something like this. Where they're not quite all the way down to zero outside the passband. So that's known as ultimate rejection. So, and it's measured in decibels. And it might be that, a filter outside of its passband might have an ultimate rejection of 80 dB, which means that it's 10 to the negative eighth of the signal strength. So 1/100 millionth of the incoming signal strength, but it's not infinity. It doesn't work infinitely well. So that's known as ultimate rejection.
And what was the question again?
What is ultimate rejection? That's a filter's ability to reject signals outside its passband. Now, there's also something called insertion loss. And basically what that does is when you put a filter in, ideally, a filter is going to be perfectly flat all the way across. It's going to have a perfectly flat frequency response. In actuality, the original signal was probably up here. So this right here is known as your insertion loss. And the way you would make up for that typically is when you were using a certain filter, you would actually add a little additional amplification to make up for it compared to not using the filter. So this is ultimate rejection. It's how much compared to the original signal it's really down. That's ultimate rejection. And then insertion loss is in the passband, how much is the signal attenuated? That's also measured in decibels. What circuits used to combine signals from a carrier oscillator and speech amplifier and then send the result to a filter in an SSB transmitter? That's a complicated way of saying what is a mixer.
Yes.
A mixer is a device that takes frequency 1 and frequency 2 and puts out frequency 3.
The carrier wave and the voice modulation.
Yep, or whatever they happen to be. If this is 3 megahertz and this is 8 megahertz, you'll end up with 3 and 8 and 11 and let's see, probably some 13 and some 14 and some other stuff that's coming out. Because a mixer is a non-linear device
A mixer is a nonlinear device that generates an external frequency from two frequencies that are pumped into it. It generates sum and difference frequencies. Something known as a balanced modulator is a kind of like a special mixer that's used for single sideband. So a balanced modulator is used for single sideband. It's a special form of a mixer. A mixer is used to convert one frequency band to a different frequency band. So in this case, if I had a 3 and an 8, my target would probably be 11. So I would be generating 11 and lots of other stuff. And what would I use to filter out just the 11 and pass that through? I would use a bandpass filter that was centered at 11 megahertz, for instance. This could also be used going backwards to take an 11 megahertz signal and combine it with an 8 megahertz signal and produce the difference frequency of 3 megahertz, which I would then also pass through a low pass filter or a band pass filter. So filtering is really, really important as far as, as far as building radios and building systems. Which of the following is used to process signals from the balanced modulator and send them to the mixer? That would be known as a filter. Okay, what circuit is used to process signals from an RF amplifier and local oscillator and send the result to an IF filter? That would be known as a mixer, right here. A mixer in reverse, when listening for audio frequencies, is known as a product detector. So basically, what it's doing is if I were to choose these frequencies that it's operating on, and let's say I had these signals that were coming in, and this would be RF from the airwaves. And I had a local oscillator, and I just wanted the audio. I would pick my local oscillator frequency very close to the RF frequency. And what that would allow me to do is do the RF minus the local oscillator frequency. That would be my
speaker. Yeah.
And that would basically just go through an amplifier and run directly to my speaker.
That's taking out the carrier wave and leaving the modulation.
Exactly. And that's known as demodulation. And that, because the thing that we're listening for is the product, that would be known as a product detector. Okay, simplest combination of stages that implement a super heterodyne receiver. Okay, so a heterodyne is a fancy word for a frequency, like a right. That would be a heterodyne, a sine wave at radio frequencies. So, in order to listen to what's coming in, a super heterodyne receiver would be RF coming in from the outside world. You have a local oscillator, which would be an HF oscillator. Then you have a mixer. All right. The mixer would generate RF at a different and predictable frequency. Typically, this local oscillator is tunable. That's how you tune your radio. You basically have this tunable circuit, which can make a changeable frequency, which you then crank into your mixer. This produces RF in a given passband, which you can then filter. And then this comes into another mixer known as a detector. And that goes into your beat frequency oscillator. And that goes into your speaker. So the super heterodyne receiver, local oscillator, mixer, detector.
What is the BFO again?
A beat frequency oscillator. That allows you to match when you're listening to it. That allows you to match the frequency that you actually want to hear. That's how you, for instance, adjust the frequency that you're listening to of your Morse code, or whether or not somebody sounds like Donald Duck if you're listening to audio. Now, does anyone ever remember like a cat whisker radio?
Oh, wow.
Yeah, my
That was a
grandfather used to make them.
that was a very simple product detector. Basically, you could actually have a radio that it actually used the power in the incoming wave to generate the audio. Was it a little germanium? What was the crystal?
Germanium.
It was germanium. Yeah, it's a little germanium
Yeah.
crystal.
My grandfather used to get germanium diodes and break the envelope open and move the whisker.
Yeah.
I had a rocket radio back when I was a kid that you could pick up radio wave, AM, FM, just off the little metal antenna on top of the rocket.
Yeah.
No batteries or nothing, just that's all it was.
Right. And it had a tiny little earphone to listen to, because that's all it had, power to power. But and the closer you were to the transmitter, the bigger the signal was.
Yeah.
Yep. Okay, let's see. What circuit is used in analog FM receivers to convert IF output signals to audio? That would be known as a frequency discriminator. So the way that an FM system works is that you basically end up with audio that, looking at the frequency, it changes the frequency from higher to lower to higher to lower in time. And this is actually done by changing something called deviation. When you speak into a microphone, it causes the frequency to shift plus and minus a certain amount from a base frequency. When it's decoded at the other end, you basically cap off the biggest and smallest signals at the peaks, and at that point you're just left with frequency, which is of a constant amplitude. This is then used by something called a frequency discriminator to produce audio. Man.
Plus FM has no static.
And FM has no static. Why does FM have no static?
You've been cutting off the extraneous signals and getting just the core.
And also, given the fact that amplitude modulation, most noise that exists is amplitude modulation. So if you were to look at a frequency spectrum of FM, it would basically look like this. That's the block you're listening to. And when you get wideband noise, it does this, like static crashes, and it raises everything. Well, since it raised everything, the underlying stuff that you're listening for is still there. So you're basically limiting it to here anyway. So the underlying stuff is still there. So you're just eliminating all the noise right off the top. Pretty ingenious, actually. Okay, what is the a typical application for direct digital synthesis, or DDS? A DDS circuit is not a dentist. DDS is direct digital synthesis. The way that it works is that you have a computer that essentially does a piecewise generation of a sine wave. And it puts out, depending on the frequency you want, pulses of a given amplitude at a specific time. So if you wanted it to generate a frequency that was higher, you would basically do this, and it would generate a shorter sine wave. Because of its computer program, it would basically generate this piecewise sine wave. And that's what direct digital synthesis is. The nice thing about that is that if you have a really fast DDS, you can make these pulses so close together that they're virtually indistinguishable from an actual analog sine wave. The cool thing about that is that, again, because they're being generated by a computer, if it's running really fast, it's also very accurate. So you get a crystal oscillator's stability, and you get incredible accuracy, and it's a variable frequency. So that's called a DDS, or direct digital synthesis. Okay, a software-defined radio. I have one of these. I love my little SDR. My ICOM 7300 is an SDR. A software-defined radio is basically where you take your antenna and you take the signal coming down from the antenna. You might do a little bit of amplification, maybe not. Typically, I think you'd probably do at least a little. And then once it gets there, you run this thing through a sampler. And this is analog coming in to digital. And coming out of this A to D sampler, you would have a lot of data, which would then be sent to a computer, a processor, which would do all your filtering and stuff like that. And then from there, it would go to your speaker or audio circuits. So what's cool about this is that it's all being done in the audio sampler and in the microprocessor. What's really cool about that is that the microprocessor is programmable. If we were building a Collins radio, no insult to Collins, they were beautiful, and somebody put in a filter with a bandwidth of 300 hertz, there would be a mechanical thing that was built in there that would have a filter bandwidth of 300 hertz. You couldn't change that filter bandwidth to, let's say, 500 hertz. It wasn't something that you could do. You'd actually have to remove it and put something else mechanical in. Well, if you're listening to an SDR, kind of like we were doing this morning, you basically can have this set to 300 hertz. You want to change it to 500 hertz. It's all being done digitally. Okay, you basically change the program and you say 500 hertz, and it basically puts it through a different series of signal processing, because it's all digital anyway. It changes the delay lines, it changes the arrival lines, and now all of a sudden you have a 500 hertz filter. You want to make it 100 hertz? Okay, you punch in 100 hertz and it changes the filter. You want to take the filter and you want to change the center point? Okay, you punch that in and you move it up 200 hertz. And then you narrow it down. It's very, very flexible. So that's known as a software-defined radio, where a lot of the functions are performed in software. Okay, so we actually have two signals coming into two signals being generated by a software-defined radio. They're known as I and Q. So I is known as in phase and Q is quadrature. Well, here we go. Here's in phase and here's quadrature. They are perpendicular to each other. Here's that 90-degree graph again. They're shifted 90 degrees apart in phase. And the nice thing about taking I and Q signals is that you can generate all different kinds of modulation techniques using the I and Q signals. So in addition to being able to decode stuff, you can actually encode things using the I and Q signals also. All right, so now it's a good segue. We're on to page 29, which is signals and emissions. All right, the first thing we're going to draw is something that should look familiar to everyone. That is the most classic form of radio modulation there is, other than Morse code. And what is that known as? Classic old AM. Where we have a carrier frequency, which is on the inside, and on the outside is our modulating envelope. So this is our carrier inside, and outside is our modulating envelope. Okay. Which of the following phone emissions uses to narrow its bandwidth? Okay, so now what we're going to do, we have to do this. By virtue of taking this AM signal and making it take up less space, in order to understand this, what we then have to do is start a new drawing. And the new drawing is on the frequency spectrum. We go from 0 to infinity. And we have our frequency and our amplitude. Okay, so this is AM. We have our carrier in the center. And we have our lower sideband and our upper sideband. And what we end up with is symmetry between the upper and lower sidebands. They contain the exact same information. Well, if they contain the exact same information, then obviously one of them is redundant if you cannot generate it. So if we then, before we go through the amplification process, if we can knock out the lower sideband, and let's knock out the carrier as well, because it has no information except it's a marker. Well, okay, let's generate just the upper sideband. This has a bandwidth of about 3 kilohertz. It takes up about 3,000 hertz wide of space. And the advantage of doing that is that it's extremely narrow. AM, all of AM is about 6 kilohertz wide.
Right.
Single sideband is about 3 kilohertz wide. Let's see. Okay, if we are amplifying single sideband, well, we're going to draw our transistor or our tube. Again, here's our amplifier. Ideally, we want to be operating in this range. This is known as the linear range. So we have our in and our out. So we can basically draw our 0 point. We'll call it our kind of like center point. And so this represents nothing out. And this is nothing in. Okay, this is one reason that certain amplifiers are not all that efficient. Well, when nothing is going in, nothing is coming out. But where is that amplifier actually sitting? What is the output level? Is it at 0?
No.
No, it's not. It's actually at 0, but then shifted up. This is known as a bias. And the reason we have to do that is if we want to maintain operation in the linear range, we have to shift it in order to operate in something called class A, to maintain it as linear. This makes it inefficient. So sometimes we will take this amplifier and we'll do this with it. We'll take one that goes like this and another one that goes like this. Let's see if I can do this. There we go. And so this is actually like 2 of them operating. So we'll have like tube A and tube B, for instance, or transistor A and transistor B. And this one operates from here to here, and this one operates from here to here. By shifting the bias points of those 2 transistors or power devices, we can make it so that the off point is actually at 0. And this is known as class AB. So, but it requires 2 different devices, and that's sometimes why it's important to have neutralization, because you have 2 different tubes, things like that. So this is known as class AB. Well, anyway, besides that though, let's look at that old class A amplifier, which makes everybody so happy. Okay, so let's say that you're talking into it and your signal gets all the way up to here. Are you inside the linear range anymore? You're yelling into the microphone. You're now into the saturation range. This will cause something known as flat topping. So basically what will happen at that point is you'll start ending up with distortion coming out of your signal. You'll take up more room. And it's possible that your signal will actually start splattering out on the band. So that's why it's important to not push an amplifier any harder than it needs to be pushed. You'll end up flat topping and going into saturation. Name of the process that changes the instantaneous frequency of an RF wave to convey information is known as FM. Instead of amplitude modulation, we're modulating the frequency. Well, we discussed phase a little while ago. That was just this morning. So we can have this signal, which looks like this, as a constant signal. We can also say that, okay, when something happens, we're going to advance the phase or retard the phase a little bit. We can actually shift the phase 180 degrees. We might see a signal that looks like this. That would be evidence of a digital signal that was using phase modulation, like a digital phase modulation. We can also do quadrature phase shift keying. That would be shifting 90 degrees at a time. If we had a receiver that could sense shifts of 90 or 180 or 270, we could actually pick up 2 bits at a time. We could actually do our encoding that way because we have 4 different states. We have 0, 1, 2, 3. That represents 4 different states. So we can have a 0, 0, 0, 1, 1, 0, 1, 1. We can also have 8 PSK, where we can shift the signal in phase 45 degrees at a time. And then of course there's BPSK, which is binary phase shift keying. That's just 180 or nothing. So, but all these are pretty interesting ways to modulate a signal to carry information, because that's in fact, I mean, that's what modulation is. What emission is produced by a reactance modulator connected to a transmitter RF amplifier stage? All right, so reactance modulator, that would be analog phase modulation. Phase modulation in a lot of ways looks very much like FM, if it's voice.
Huh, we picked one up.
That makes sense?
We're down to 18.
Okay, how is an FSK signal generated? Okay, so FSK is kind of what I just talked about. That's frequency shift keying. Basically, frequency shift keying, you have your starting frequency, and then you have, when something happens, you shift the oscillator to a different frequency. So they go back and forth. This is something that you'd find in something called radio teletype. And that's known as FSK. Okay. Again, there's PSK, which we definitely just did. That's phase shift keying. Again, there's BPSK, QPSK, 8PSK, and so on and so forth. So let's look at QPSK 31. They seem to focus on this on page 31 of the, oddly enough, on page 31, there's a mention of it. QPSK 31. That's a very narrow bandwidth mode. It takes about 31 hertz of bandwidth, which is insanely narrow. It also has error correction, and it's also sideband sensitive because it actually matters whether you're shifting 90 or 270. And if you have the wrong sideband shifted, you'll go 90 this way, but it really went 90 that way. And you'll get the data wrong. Okay, FT8, a mode called FT8, which is very, very popular right now. It's very good weak signal mode. People use it for moon bounce and other cool things like that. It's a mode of eight tone frequency shift keying. So you have a base frequency, and then depending on the data that comes in, you can go to 1, 2, 3, 4, 5, or 6, or 7. So you basically, if you look at it over time, if you can kind of picture what a player piano strip looks like, you know, it has some of this. As it goes through time, you can see the different notes being hit. That's sort of what PSK looks like, although
or what FT8 looks like, although it's only one node at a time as it advances through time. Okay, it also is a very good mode for poor signal to noise ratio. So if there's a lot of noise, FT8 is great for that. All right, page 32, frequency mixing. What is another term for the mixing of two RF signals? That's known as heterodyning. I have a really good example of that. I was once, okay, so we have our repeater when I was in college with a transmit frequency of 144.89. And we were getting our output frequency of 145.49. Sorry, this is the transmit frequency. And this is the receive frequency. We were getting our transmitted signal somehow on our receive frequency. Somehow. Well, it turned out that we also heard some amplitude modulated AM radio stations. What we discovered was that within eyesight of us, because we were on a hill, there was a station at 980 AM and another one at 1580 AM. And if you figure out what the difference of those is, it's 600 kilohertz. And if you look at this, the difference between our receive and transmit frequency was 600 kilohertz. What was happening was that there were some rusty bolts up on our tower that were taking these two signals, mixing them together and generating a 600 kilohertz signal, which was then combining with our 145.49 signal and making a signal on 144.89, which was locking up our repeater.
Huh? Wow.
Yep. And all it needed was something to do the mixing. And since mixing is nonlinear, that requires like a diode. And guess what? A rusty bolt makes a pretty good diode sometimes.
Wow.
Yeah. And there's nothing you could really do about it except replace your hardware. But
Yeah.
it took us a year to find it.
Huh.
Okay, and that is known as heterodyning, the mixing of two signals together to make a new one. What's the combination of a mixer's local oscillator and RF frequencies found in the output? That's known as the sum and the difference of the two. So if I have frequency A and frequency B, and they both go into a mixer, I'll get A plus B, A minus B, B minus A, 2A, 2B, 2A minus B, 2A plus B. Well, what do you notice about this? It's a mess, right? It's an absolute mess. So after doing mixing, it is very important to use a filter. Now, it might also be that two of these combinations, for instance, A minus B or sorry, A plus B or 2A minus B could be the same frequency. That might be a problem. So at that point, you have to pick what your frequencies are. This one you can't control. This one you can control. Well, if you can control it, then you can pick it so that your filter will work properly and not get slammed by other frequencies. And actually, if you have a radio that is in a high RF environment and the filtering is not particularly good, sometimes you'll actually hear something called aliasing, where you find something that you don't expect it to. And that's a result of the mixing process. Okay. Which mixer input is varied or tuned to convert signals of different frequencies to an intermediate frequency? The one that you can control, which if I draw this right here, the one that says can, this is known as the local oscillator or LO. That is the frequency that you can control. Again, local oscillator, because you have local control of it.
Let me see if I appreciate. You're saying the carrier wave the constant, but the modulation frequency could change?
Say that again?
I want to see if I appreciate this. The carrier wave would be the constant, and the modulation, the voice would be changing the frequency. That's where you can adjust it.
No, what I'm saying is, let's say that what you have outside, we'll call this frequency A, is actually not a frequency at all. It is your antenna. And your antenna is picking all of this stuff up on all these different frequencies, right? That is the uncontrolled frequency coming in. And the controlled frequency is this one that you can control. That is your local oscillator. So what happens is that you then mix this controlled frequency with this whole mess coming in from the outside world. And that will make a bigger mess. Right? But if you've picked it right, let's say you did some pre-filtering, so you can take your inputs, you can take what's coming in off the antenna, and you just hook up like a pre-filter that pre-filters just this range. And it blocks out almost everything else because you've done a good job in filtering. Well, you now have this block of frequencies mixed with a frequency that you can control. So let's say this is 11 megahertz. Right? Let's say that you're running it through an 11 megahertz preselector, and you've tuned your local oscillator to, let's say, 29 megahertz. And okay, well, you have 11 and 29. I'm going to add them together, and I'm going to target 40 megahertz as my output frequency of my local of my mixer, and I'm going to run that through a filter that allows only, let's say, 39 to 41 megahertz through.
Right.
So that if there's the difference, it will also have 18 megahertz coming out. The 18 will be somewhere way down here. The 40, the 29 that went in will be down here. The 11 will be down here. Now, the only tricky thing is, let's say that I have 29 and 11, right? What's another way to generate 40? If there's something unexpected up here, what minus 29 gives you 40?
11.
That would be 69.
Oh,
because then I'd have 69 minus 29 is 40. So that's when you'd start getting the aliasing of this 69 megahertz signal. Essentially, this would be called an image. This would be called an image effect, where you would have a secondary signal that is coming in from somewhere you completely don't expect it to. That would then also come in on the signal. This can actually happen if you live right near, let's say, a big FM transmitter, and you don't have filtering thrown in. So that would be what I would call an unexpected effect. So image response in your receiver, it's called. And oh, well, there you go. That's actually the next question. If a receiver mixes two different frequencies, and you'll end up with two different frequencies, one of which you expect and one of which you don't, you end up with something called an image response. What process combines two signals in a nonlinear circuit or connection to produce unwanted spurious emissions? Okay, that would be known as intermodulation, where you basically have your in, and here's another in, and here's an out. If you have two signals coming in, then they can actually result in something very unexpected coming out. And that's known as IMD, which is intermodulation distortion. What is the stage in an FM, in a VHF FM transceiver that generates a harmonic of a lower frequency signal to reach a desired operating frequency? Okay, so let us say that you have an FM transceiver that is designed to operate on 146.52 megahertz, which is the simplex calling frequency. And you have a frequency multiplier of 12 times. So that means that you're actually operating on 12.21 megahertz inside your radio. And you run that through a multiplier to generate that. Well, the tricky thing here is, let's say that you want a total of 146.52 plus or minus 5 kilohertz. And that's known as deviation. How far off you want your signal to be. Well, if this operates 146.52 plus or minus like that, and this is operating at 12.21 minus plus like that, then this whole thing is going to get expanded by a factor of 12, including the deviation, which means that you need 1/12 of the 5 kilohertz deviation, which is about 416, 41, hold on, let's see, 5 plus or minus 5 kilohertz. Yeah, 416 hertz. So basically, you're gonna, since you're going to be doing a frequency multiplication on the whole thing, if you're modulating down here at a lower frequency, it has to be a narrower copy, because when you expand it, the modulation deviation will expand as well. Everything gets 12 times bigger. Okay, let's see. What's the total bandwidth of an FM phone transmission with 5 kilohertz deviation and 3 kilohertz modulating frequency? They simply add together. So we have 5 kilohertz, 5 kilohertz, and then 3 kilohertz on that side and 3 on that side, and you add them all together and you get 16 kilohertz. That would be your total bandwidth. Okay, we're into digital stuff. The approximate bandwidth of a PACTOR3 signal. Has anyone used PACTOR? I've never used PACTOR either. At maximum data rate, approximate bandwidth of PACTOR3 is 2300 hertz. It's just something you got to memorize. Why is it important to know the duty cycle of the mode when you're transmitting? So, okay, a lot of equipment is not designed to operate at 100% duty cycle, 100% duty cycle transmit. When I'm doing Morse code, my duty cycle is at worst 10%, maybe 20, maybe. If you're doing FM, conceivably it could be up to 50%. You know, you're talking half the time and listening half the time. Some modes are even higher than that, you know, if you're transmitting full power all the time. So FM, teletype, those are typically very high duty cycle modes. A lot of radios are not designed for full power all the time. So if you are doing that, you need to drop your output power so that it doesn't generate so much heat that it kills your equipment. Symbol rate and bandwidth. Higher symbol rates require more bandwidth. Basically, the more information you're sending across, the more room it takes up on the band. And why is it good to match receiver bandwidth to the bandwidth of operating modes? It results in the best signal to noise ratio. And we will talk about that in a minute. Okay, digital emission modes. Okay, PSK 31. PSK is the approximate, is phase shift keying. The 31 represents the approximate symbol rate. So 31, PSK 31 is 31 symbols per second. Now, there's also a mode called PSK 63. What do you think the 63 does? 63 symbols per second. Which one takes up more room on the band? Yep.
63.
The 63. There's also a PSK 125, which takes up twice as much as the 63. There's also a PSK 250. So the reason that people use PSK 31 for
for talking back and forth is that most people can type at about the same rate that PSK sends characters. PSK uses something called varicode. If you've ever operated PSK, people will say, don't use uppercase. Do all your, even though you're used to typing uppercase, don't use it. And that is because varicode, which is what PSK uses, makes uppercase letters have a longer character. So it actually slows you down. It slows down the transmission rate. So that's why people use mostly lowercase when using PSK. A Baudot code, baud, we've known as baud rate. Baudot code is a 5-bit code with additional start and stop. So that's baud. How are two separate frequencies of FSK or frequency shift keying identified? For those of us who have done RIDI, they're known as mark and space, and they shift back and forth, just back and forth, two different frequencies, known as mark and space. And those all go all the way back to when teletype was teletype and not even on radio. It started off on wires and then radio, and then it took over on radio. A digital mode used for low power beaconing for assessing HF propagation is known as whisper, which is basically a one-way transmission mode by which people will set up beacons that just send out signals around the world at very, very low power periodically. And other stations will that are listening will automatically record it and post those observations to a central server. This can actually be, it's very similar to something that looks just like this. So this is PSK reporter, and it's listening to packet and FT8 and CW and other different modes. This is basically showing all the propagation that's been heard from FM 19, which is in Maryland where I grew up, over the last 15 minutes. So all the different stations that are operating and receiving that are reporting what they're hearing automatically. Here's what, wow, look at that. Lots of stuff into Europe today from the West Coast. Impressive. I guess I know what I'll be doing after this.
Good.
Okay. So that's known as whisper, WSPR. What part of a packet radio frame contains the routing and handling information? That would be known as the header. Header is basically the stuff at the beginning, telling everybody where the packet is going. Pactor, a NAC packet, is NAK, which means no acknowledge. So that means I didn't get it, please send it again. So it's asking for a retransmit. If you're using something called Pactor or Winmore, and you have too many attempts at trying to get information across and it keeps failing, basically it's a peer-to-peer, point-to-point connection, and the connection gets dropped. How does a receiving station respond to an ARQ mode? ARQ means automatic repeat request. It basically means I didn't get it, please send it again. How does forward error correction allow a receiver to correct errors in received data packets? Okay, FEC, forward error correction. So let's say the simplest form of forward error correction is I'm sending 3 bits and I'm adding, I'm not going to add anything. So 1, 0, 1. Okay, it goes through this channel as it's called, and we receive 0, 0, 1. Does the receiver have any way of knowing that that signal wasn't right? Any way at all?
Nope.
Nope, not a thing. So all of a sudden, this was a number 5, and now we recorded it as a 1 with no additional information saying it was wrong. That's how you get errors. Okay, but now let's say that I am going to, as a sender, look up the number of signals that I sent out that were 1. And if it was an odd number, I'm going to add a 1 to the end of it. And if it was a zero, if there was an even number, I'm going to add a zero. Well, there's a one, there's a one. That's two. So that's an even number. I'm going to add a zero. All right. This is known as a parity bit. If people have ever heard of something called parity, parity. Okay. So that goes through. The first bit gets trashed. It gets copied as 0, 1, 0, 0, 0, 1. Well, by this protocol, what is the total number of ones being sent? It has to be an even number. It has to be 0 or 2 or 4. No way, no two ways about it. So how many ones were there right here?
Yeah,
one. That is an odd number. That is a no-go. That means something got trashed. We don't know which, but something's not any good. It could have been the parity bit, but we don't know for sure. All we know is that that is no good. And this is known as error detection. So if we were to add more bits and make them more intelligent, to say that they were somehow like a combination of bits that went into additional characters being generated, we could actually do error correction. Like if we were to send the entire thing 3 times. Okay, well, we just look at this and we said, okay, well, we got 1, 2, 3, 4, 5. And okay, well, which one did we get? We know there are 3 bits at a time. We got 101 and 101. Those match, and this one's close. Well, we know it's 101, right? Okay, but what was the thing that we just killed? What was the information that we were sending?
The first part, wouldn't it?
Yeah, we were just sending the first part, but to make sure that it made it through, we sent it 3 times. What did that just do to our data throughput?
Multiplied it twice.
By 3 times. We sent it 3 times. So it cut our data by 2/3.
Okay.
So that's what you lose when you write in all this error correction. So that's the trade-off. And that's why sometimes, being able to actually correct the error, well, it's not really worth the effort. It's more worth the effort just to know that it failed and say, please send it again. Okay, so transmitting redundant data. Okay, waterfall display. A waterfall display is something that looks like a player piano tape over time. A waterfall display will give you a vertical representation of what signals look like on the band. And I'm going to show that to you in just a minute after we take a short break. But a waterfall display gives you frequency this way and time this way. And the intensity of the signals give you amplitude. It's a very, very cool way of looking at what's happening on the band. And that's known again as a waterfall display. What's indicated on a waterfall display by 1 or more vertical lines, sometimes you'll see something that looks like this. Basically somebody, that's overmodulation. Somebody's really loud and either overloading your receiver or overloading their own transmitter and causing it to transmit sidebands when they shouldn't. On what band do amateurs share channels with the unlicensed Wi-Fi service? That'd be 2.4 gigahertz, also known as 802.11, if I'm not mistaken.
Wireless on computers.
Yeah, exactly. And that's why it's so easy for hams to take old routers and repurpose them as ham radios that can then be used to transmit data. You take a router and you dump new firmware into it, and now it's a self-healing router that's part of a big network. That's the whole basis of this thing called ARDN, AREDN. Okay, 5-minute break, y'all.
Yeah.
Okay, excellent. All right, can everybody see and hear that?
Oh, yeah.
So this is a 0 to 30 megahertz. Notice it's waterfall. 0 to 30 megahertz display of an SDR in the Netherlands at the University of Twente. What's cool about this is that it's a full 30 megahertz picture all at once.
Oh, that's the same thing that I see on WebSDR.
It is the #1 hit on WebSDR.
Yeah. I
And
use that a lot.
so what we're going to do is zoom in on 20 on the, notice it says 20 meter amateur band. S55X. And we're going to play a little with bandwidth and why bandwidth is important, picking the right filter and stuff like that.
That's what I'm just now learning how to use on all that.
Isn't it cool? Look at that.
Yeah.
Oh, it's wonderful. Absolutely wonderful.
This is what's cool about this is that my ICOM 7300 does this. You know, it's so many leaps and bounds beyond the first radio that I had 35 years ago.
Yeah.
Just a crazy question, Scott.
Yep.
Cool.
Go for it. I want to hear the crazy question.
Crazy question for me. Yeah, I bought an 891.
Yep.
Yaesu 891. So, you know, which I don't have the waterfall to see what's
I know.
where. So, in would I be able to use like WebSDR to look in certain areas to see what there is and trace down a band?
I mean, I use WebSDR just to see what's going on.
Oh, okay. So yeah, and then on something like that, you could actually go into those frequencies then and possibly get into it on your radio.
Oh yeah, sure.
Okay.
I mean,
yeah,
I've actually used a WebSDR to hear myself.
Oh, have you really?
I have.
Let me see how your signal is. Sure.
Yeah, you can monitor your own signal as received.
Right. Yeah. See, that's what I was thinking of doing with it because I don't have a waterfall on a 891.
Well, let's see if I. Okay, so here's FT8. Let's crank that up. Let's get the whole band. That's FT8. Okay, notice we can actually see the band.
Yeah.
And typically when you're listening, FT8 is designed such that you're really able to listen to everything at one time in one single sideband 3 kilohertz passband. And what's cool about the software is that it decodes everything it hears. So because each one of those stripes is a separate signal, you might be able to decode 25 or 30 signals at once, which is kind of cool. Oh, and here's FT4, which sounds like aliens to me. Another digital mode. And of course, the oldest digital mode. This is actually a digital mode. It's on-off keying or OOK. The unique thing about it being that you can decode it by ear. So
as text, we can't use FT8, right?
yeah, you can. Depends on the band you're using it on. You can use it on anywhere on VHF, UHF that it's used. You can use it on 10 meters.
Within that 10.3 to 10.5?
Believe so. 28 100 to 500.
That's what I meant.
Of course, you know, that's why you're looking at upgrading, because, you know, it's, you know, there's whoa. Who's he talking to? I thought I heard 9K2.
QSL, my friend. Thank you for the signal report and short QSL. Oscar November 1 Alpha Juliet 9K2 JJ Fish 73 match.
Yeah, he's in Kuwait. But of course, this is what happens if you do it backwards. That's why it's important to get the sideband right.
Yeah. That's great to use that. I play with it all the time.
Yeah, and there's a lot you can learn from this. I mean, for me, actually getting a radio that would be able to just give me a waterfall display. The first time I used it, it was like, oh my God, I'm not blind anymore.
Yeah.
Because I'd been blind on the air my whole life. The only way that I would find anything was by tuning around. You know,
Right.
spin the knob and look and listen for something. I could see when there's something. Now I can see when there's something popping up. You know, if I want to call CQ during a contest, I don't have to wonder where to put it. I can look and see, okay, there's a big notch. I'm going there.
Gotcha. Yeah, that's the one thing that I don't have on this one, but
yeah, but you know what? That's a good radio to start.
Yeah.
You know, that's the other thing that I got my license in 1984. And since that time, I have probably owned just HF radios, 50 different models. So
that's what's called radio poor.
It is, but you know what? I ended up at every point in time, I either tried or owned something that was something that I could afford. That the thing is that I could also sell if I wanted to get rid of it if I didn't like it that much.
Right.
Right. I never bought anything new, except for the 7300. I bought the 7300 new. I've never bought another HF radio new.
What would you recommend, Scott, for because I don't have an HF radio. I just have my handheld Yaesu FT2D, which is a really good handheld.
Yeah, it is.
But I don't have. I was wanting to find something that's affordable for me, to tinker in the HF.
Okay, well, a big part of it is the same decision that you're going to, the same decision that everybody comes across, which is, you look at, I just got this catalog, and this catalog is full of dozens and dozens and dozens of pages of HF rigs. And
that's the Christmas catalog.
It is, and so here's what I recommend. If you're not going and you can get away for a weekend or at least, a day, go up to CPAC next weekend.
Right.
Ramon, go up to CPAC if you can for a day.
I wish.
I
On
know.
Saturday,
Well,
I'm leading some community service here in Florence, and then on Sunday I preach.
How about Friday?
So I have literally all Sunday.
How about Friday?
Friday would be preparing all the admin stuff for the community service. Literally, my
I know.
weeks have been so stretched thin that I'm like, I want to get my general. I want to go on field day. I want to do these things, but it's just like
one thing at a time.
One thing at a time.
So, I mean, a big part of it is, you have to look at, you have to look at what your expectations are and what you're going to be happy with either permanently or temporarily. And, once you have an idea, I mean, the other thing to do is ask at the club, ask at your local club, hey, does anybody have an HF rig I can borrow and try out just so I can get on the air? I mean, if you lived here, I'd loan you a 718, right? ICOM 718 right now. If you get to Eugene, I'll loan you my ICOM 718. So
that's what I did with talking to people, so many people about it.
Yeah.
And I finally just went with the 891 because I figured it's got all the bands and that'll give me a choice of what I like. It's going to be there.
Yeah, I mean, but I've got an ICOM 718 that's sitting on my shelf doing nothing. You know?
See, the problem is a lot of the guys here, you know, I retired early from the Marine Corps and I live off of my pension, and that's what allows me to retire.
Yep.
I mean, do what I do. So I have a very limited income, even though my retirement's a decent retirement. Every month, every penny gets calculated, and
Yep.
everyone's like, "Yeah, you need to get this FM radio with this. It's only
Yeah, I know.
$17.99. Oh, this one's $2,000, but it does everything." And I'm just like, well, I just need something to hook up to my truck to tinker with, especially since I travel full time and I'm always on the go. It'll be really fun to be mobile, because a lot of times everyone's like, well, the moment you say you're mobile, everybody and their mom gets on the radio because they want to know where you're at, where you're going. And then
Yeah.
it's really fun to communicate with everybody, other hams when you're traveling. And I'm just like, I just need something basic that I can hook up to my truck and tinker with. That's not going to cost me $1,700, $2,000.
I've never spent more than $800 on any piece of equipment. Not even once. Actually, 900. I think the ICOM was 900. That's the most expensive thing I've ever bought.
Shopping.
I know. Well, but you know, like seriously, Ramon, if you get to Eugene, let me know. I'll just let you borrow I'll let you borrow my 718.
I'll be grateful. I'll let you know if I come up there.
Yeah. All right. You guys ready to keep going? Deb, I saw you had your hand up. Hello, Deb.
It's irrelevant to everyone else. I'll just email you.
Oh, it can't be that. Is it that irrelevant?
I was just going to ask if there's any sound equivalent to the waterfall, which I'm sure there isn't, but I just wanted to ask.
I have no idea. I mean, the part of the problem is when you say sound equivalent, I mean, you can open up a receiver big, you know, big and wide and listen to a whole big pass band. I mean, that's the only thing you'd get. I mean, to know, like, if I were to listen to, well, let me go back to the web SDR. Here, let me bring this up. And I know you can't see it, but you can hear it. I mean, you're basically, and if I go to the band, let's here. I'm listening to about 10 kilohertz at once now. That's about as wide as I can make it. But I mean, I can tell the difference what I'm listening to. You know, I mean, I hear a lot of signals in there. And I can, except for the really high pitched ones, I can't really pick them out as far as what they're saying. But I mean, being able to listen to 10 kilohertz, I don't know how you would. I mean, I guess it's possible, but that would overstretch the range of hearing. You know what I mean? I mean, because what would you translate it to?
Yeah, I agree.
I mean, it's possible. I think that something, you know, what would be interesting to do? Something like that would work as far as like if you did like a frequency compression, where you could take an entire band and compress that down. That would work. That sounds like a project for somebody. Actually.
I have a question when you're ready.
Yeah.
When I first got my license, thanks to your instruction, I walked into one of the ham radio shops, and the first thing they said to me, everybody, remember, as a technician, you can only go on the 10-meter band. Okay.
That's not true.
Yeah, exactly. When I got your charts, it looked like I had a great deal more available. So I was just wondering why I got that.
Well, if you're willing to operate CW.
Oh, okay.
on HF, I mean, you still have all the novice frequencies on 80, 40, and 15 meters.
That's what I thought. Okay, yeah.
I mean,
I'm
it's
looking at the
CW
chart, I
only,
just
but
went, wait a minute.
But I mean, there's actually, I mean, that's where I cut my teeth. So.
Oh, I gotta get my antenna up.
Thank you.
All right, we're into antennas and feed lines. Possibly my favorite part. Okay, which of the following factors determines the characteristic impedance of a parallel conductor antenna feed line? Okay, so what we're going to draw is two wires. Okay, what do you notice about these two wires? If I drew them correctly, they are what?
A dipole?
Nope. They hopefully are parallel.
Okay.
Right? And they are separated by a fixed distance. Okay. So what do you have? What is it called when two things that are made of metal are a fixed distance apart? They form a capacitor.
Yeah.
Right. So you have a capacitor here. And what do you have along the length of a piece of wire? Every piece of wire also functions as Inductor, yes. So you can actually draw this piece of power of transmission line as an infinite series of inductors and capacitors that are just grouped together. Well, if you have inductors and capacitors, you have an impedance.
Impedance.
Yep, you have a resonant frequency. So basically that defines because of the spacing and the diameter of the wire, that determines what the capacitance and inductance is. So the impedance of a parallel line is defined by its geometry.
Now you're talking like ladder line would be that?
Yep, exactly that.
Okay. That's what I was going for.
Okay, now coaxial cable is actually the same, but different. All right, so here's coaxial cable. You've got our outer conductor and our inner conductor, right? What do you notice we have between the outer conductor and inner conductor?
The shield?
Well, no, the shield is on the outside.
Oh, sorry. Yeah.
What's between the outer and inner?
That'd be the ground.
Nope, dielectric.
Oh, dielectric. Okay.
Right? This is plastic or some kind, or, polyethylene, or could be air. But basically, it's a gap. Okay, so if you look at it, you have as the entire length, you have two wires or two conductors, except they're cylindrical, separated by a gap. This is a capacitor. And you have the center conductor, which is wire, and the outer conductor, which is essentially a cylindrical wire. Those are inductors. So once again, what do you have? Capacitors and inductors.
Yep.
So what defines the characteristic impedance of coaxial cable? That would be the diameter and the dielectric and the spacing and the diameter of this. If the geometry, the tricky thing is if the geometry is maintained, you just scale it up, it's exactly the same. Because it's not impedance, it's characteristic impedance. No matter how long the cable is, the impedance is a characteristic function of how you built it.
Now that would vary with the distance between the diameter of the.
If I were to take, yes, if I were to leave the conductors the same sizes and make the cable bigger, I would decrease the capacity.
Yes, that's what I wanted to. That's what I was trying to get to.
And I would change the characteristic impedance of the cable.
Yes,
now,
okay.
if I increased everything at the same rate, right? If I increase everything proportionally, then it would be the same.
Okay. Yeah, that makes sense. That's what's kind of thrown me on that for a little while.
Well, the fact that it's not an impedance, it's a characteristic. Literally, it's that. It's, in one section of this cable, this is what the impedance acts like. And if I take that and put it in series with another, it doesn't add, it just is a longer copy of the same thing. So most coaxial cable is either 50 or 75 ohms. In the radio world, it's 50 ohms. In cable TV, it's 75. What can cause reflected power at the point where a feed line connects to an antenna? If you have a differential between your feed line,
let's say this is 50 ohms and your cable and your antenna is 75 ohms. This would be a mismatch right there. You will have power that goes out and power that gets reflected. I mean, it's kind of like the analogy I give is you tied, here's a doorknob, and you tied a jump rope to the doorknob and you slammed the door shut. You kept it shut, and then you whip the jump rope and it goes like this. What happens when it hits the doorknob?
Stops.
It doesn't stop.
Oh.
Where does the energy go?
Oh, into the doorknob.
What if the doorknob doesn't move?
Ah.
It goes like this.
Yep. Bounces back.
It bounces back at you.
Right.
That's right. So that's
like
exactly
a rock in the water. When you throw it in, it's going to hit the shore and reflect back.
That's right. Okay, so standing wave ratio will result when you get 50 ohms tied to a 50 ohm non-inductive load. You have a perfect match of 50 ohms going to a 50 ohm load. All the power will go out if this is 50 ohm cable. And essentially it will look like the cable goes on forever and nothing ever comes back.
Is that when you get an SWR of 1-to-1?
That would be a perfect 1-to-1. So now let me ask this question. If I have a 50 ohm non-inductive, so it's 50 ohms plus J0 ohms, right? It's a perfectly resistive load. Does my cable care if this is an antenna or a dummy load?
Doesn't matter.
That's right.
No,
Now,
no, it doesn't matter.
who cares?
Well, you're not going to transmit on the dummy load.
That's exactly right. So let me ask, if you find an antenna that they say is broadbanded and has an SWR of less than 1.5 to 1 from 0 to 30 megahertz, how well do you think it might actually work? If it's, it says tune free.
You're going to lose some signal.
I don't think it'll work well.
It's not going to work very well because you know what works really well as providing a really good SWR on all frequencies, and you don't need to tune. That would be a dummy load.
Okay. Right.
So you have to, when somebody comes up with something like that, like there's I think Comet makes an antenna. It's like a CHA 250. It has this transformer with this big ass heat sink in the base and then like a 16-foot vertical section. And it's got this is kind of like a clue. It's got a transformer in the base with this really big heat sink on it. And it says no tune wideband. It's like, well, okay, what is that transformer with a really big heat sink? Why is there a really big heat sink on it?
Absorbing the excess signal.
Well, yeah, exactly. Because if you have 100 watts going in, where does the 100 watts end up eventually? Somewhere, right?
Yeah.
It goes somewhere. If you have 10 watts going out, where does the other 90 watts go?
And who's it going to?
Yeah. It's heating the cable, it's heating the resistor, it's heating the transformer. It's coming out somewhere.
Turning your radio.
Well, right. You can't. Well, no, it's a good match. It's not coming out of the radio. The 90 watts is getting dissipated somewhere.
Yeah.
Ideally, you want that up in the sky as opposed to warming your antenna.
Chameleon antenna is the same way. I think Catherine had one of those.
Yeah. I mean, it works.
Huge load at the bottom.
Right. I mean, it works. It does work. The question is, how well does it work? And that's when you start looking at, design trade-offs, and when you start looking at modeling and figuring out where your signal's actually going or if it's going. And, if you have a lot of excess gain, you're only 10 miles from who you're trying to talk to, big deal. It works great. But if the difference is that you're trying to talk from like, here's the Earth and here's like person A and person B, and your path loss up through the ionosphere is negative 140 dB. And okay, well, your minimum discernible signal is minus 136 dBm. and you put up an antenna to make that path, you need to have at least +4 dBm coming out on this end. And, you know, okay, well, if you have an antenna that's just like a plain old vertical, but it's a tuned vertical, then yes on that. But the other one, it doesn't make it because there's enough loss that it doesn't work. So, you know, the question is, what's your goal? The question with all of this is, what's your goal? You know, that's why people put up, that's why people put up 100-foot towers with stacked Yagis on them, because they might get you an extra 20 or 30 dB of gain. That's the difference between enjoying yourself and getting really frustrated in some cases.
Scott, I've got a 40-foot dipole I'm installing in the attic, and they indicated I have to be careful to get a antenna tuner with a 10-to-1 SWR correction because of it being in the attic.
Okay.
So that fits what we're saying then.
Yeah.
Okay.
Yeah. I mean, you just have to have realistic expectations. You
So
know,
you'd be better off, in most cases, be better off like what you told me and others, choose your antenna to match what you want to do.
to a certain degree, yeah. I mean, but part of it also is you put up what you can.
Right.
And then it might be that you have to get smarter.
Yeah.
I've got
the area to put it up, but it's like my wife doesn't want a big, huge antenna in the back.
Right. Well, but in my case, what that meant was that I hardly operated any phone.
Right. I
really went hardcore into Morse code because I wanted to make contacts, and I knew I had attic antennas, and even from my car, I had a screwdriver with an 8-foot whip on it, and I made hundreds and hundreds and hundreds of contacts on that antenna, most of which were CW, even while I was driving, because that's what worked. I mean, it was really hard to make voice contacts.
Talk about texting while driving, really.
I know.
Yeah, really.
Paddle on the passenger seat.
Easy.
Wow.
Paddle on the passenger seat and 60 miles an hour and a stick shift. So
multitasking.
Yeah.
Hey, well, going back to Merlin's comment, what was said about having a dipole in your attic, but you needed a 10 dB box or something? Is that a match?
Well, you need an antenna. You really want to have an antenna tuner that can handle the kind of mismatches that you might get.
Okay.
I mean, let's just draw a dipole, right? A half-wave dipole is going to be about 70 ohms, right? A half-wave dipole in free space, okay? Let's say you have room to put up one antenna. This is no longer on all, if you're going to use that one antenna on all bands, that is not a half-wave dipole most places, right?
Okay.
That's going to be whatever it is. On some bands, it might be 3/8 of a wave. On another band, it might be 0.41 wavelength. On another band, it'll be 2.6 wavelengths, right?
Yeah.
So you would have to go through and, okay, I'm going to figure out what the impedance is supposed to be on every one of those bands. What is that going to do for you is the question. And the answer is, okay, it's a good academic exercise, but practically speaking, it does you no good whatsoever. Because you're still going to use the antenna, right?
Yeah.
Is it going to tell you don't use the antenna? No, of course not, because it'll work better than nothing. So what that really means is that you have this mystery thing up there. Not only that, it's in your attic. Okay, so now you have ductwork, and here's your roof line, here's your chimney, and here's your soffit vents, and there's some more air conditioning ductwork. How exactly have you defined whether or not your antenna is coupling with all of those things?
Yeah.
And the answer is you can try, but good luck. So
this particular one has 3 distinct lengths that come with it for the different bands.
Okay.
And then it comes down into the center with, and it's got some very interesting coils at the end, I think, to enhance the signal.
Okay.
But yeah, that's why I needed, the 10-to-1 ratio to account for all the potential interference.
Right. Well, and the fact that you are not going to just limit your use to those bands.
most likely. I mean, if you want to get on 30 meters and it doesn't tune, it's not designed for 30, are you not going to use it? Are you going to say, I'm not going to try? Of course, you're not going to say that. You're going to try. Especially if, you know, there's some station in a country that you've never talked to before, and you got to try, because you got to try, right? So you're going to try to tune it. You're going to try to tune it.
Never say
and,
die.
Yeah. Well, and so if you, let's say that by the time your signal, by the time you get down here, it's 275 ohms, right? And you're at 50 ohms going in. Well, that's almost a 5-to-1 SWR, which means that if you tune it, it's still going to be really pissed off up top. You know, your signal is going to be bouncing up and down the coax a lot. There's going to be a lot of signal loss, but it's not infinite signal loss. You still get some signal out. It will still work. So having an antenna tuner that gives you a wide range of basically just being able to do something is actually really important, especially if you're doing a compromise.
In this case, the Z Pro 11 antenna tuner had the 10-to-1 ratio.
Yeah, that'll work great.
Yeah, so it's careful to buy it. You spend a lot, but yeah.
What is it, about 250 now?
Yeah, something like that. Exactly.
Totally worth it.
Yeah.
Totally worth it. It's automatic and it's a wide range. LGG has made good stuff for 30 years.
No, yeah, you recognize the brand, yeah.
Okay, let's see. Where were we? Let's see. What might cause reflected power? We did that. 50. Okay, 1-to-1. Okay, how do you reduce standing wave on an antenna feed line? If you match the antenna, feed point impedance to the transmission line, you don't get any waves coming back. Okay, so if you have an impedance mismatch, and let's say you have 50 ohms going up and your antenna is 200 ohms, your mismatch is 4-to-1. Now, interestingly, if you take this and you make this antenna 12.5 ohms, you still have a 4-to-1 mismatch. You take the bigger one and divide it by the smaller one. That gives you your answer. If you have a 10 ohm antenna, then you have a 5-to-1 mismatch. Your SWR is 5-to-1. Okay, this is an important distinction. I'm going to read this verbatim. If the SWR on an antenna feed line is 5-to-1 and a matching network at the transmitter end is adjusted to 1-to-1, what is the resulting SWR on the feed line? This is a very, very, very important conceptual problem. My SWR is 5-to-1. I have my antenna network here. I've matched it. I'm 1-to-1. What is my SWR on the antenna?
5-to-1.
5-to-1. That's right. In other words, having a good match down here makes your transmitter happy, but it doesn't do anything as far as solving the problem up there. It can't. It just means you're not going to blow up your transmitter, and you're going to at least be able to try to put lots of power into it. So that's it, Merlin. That's actually really important because that's what they're telling you to do. But the important thing to remember is that it doesn't actually fix the problem.
Right. It just makes it so the radio can accept it.
That's right. That's exactly right.
So I haven't enhanced my sensitivity at all.
Right. It just makes it so that at least it's matched properly. At least there's efficient power transfer between there and there.
Well, does that mean you should have two matching devices, one at the antenna and one at the radio?
Actually, you should really just have one.
To get the right antenna.
or you just get your antenna and you have an automatic tuner. You may actually want to consider doing this. If you can do it remotely, put it right up there at the antenna.
In this case, right at the attic?
Yes, put it in the attic.
So in other words, attach that. So the tuner actually goes up in the attic, not next to the radio, if you're saying this right.
If you want to do it so that you minimize your loss, then it's 50 ohms all the way up to the tuner, and the tuner is right there at the in the attic at the antenna.
Yeah, it's an automatic. Yeah, so it's all set auto. Yeah, that sounds like a solution.
Yeah.
You're tuning the antenna specifically instead of having it make the radio happy. You're making the antenna happy for the radio.
Right, I've got plenty of power up there. It's just putting the connector right there.
Yep.
And then setting the switches so it's auto and we're good.
Yep.
Okay, bingo. Thank
They
you.
actually might make a remote tuner.
Time to check.
Yeah. I know that a lot of companies will actually make a tuner that is remotable, you know, that you can actually put outside, like in the weather, so that it goes up on your tower, just like they do with like an antenna switch, a remote switch, so you can run just one cable up to it.
Yeah, well, the homeowners association wasn't going to allow an outside antenna. So
Well,
they
right,
dictated
right.
everything.
But I'm saying that, you know, they make waterproof ones too, so.
All right.
Well,
Okay.
have you guys seen the antennas? They're a couple $100, but they go on your vehicle, or I'm sure you can use it in your house, but it's an automatic adjusting. So it goes up and down to find the right ratio on its own. The moment you connect, the antenna goes up and down. I saw it in a magazine and I thought it was the coolest thing, but they're like $300, I think it is.
I've got a screw. Yeah, I've got a screwdriver antenna that does that. That's what I've used on my car. And essentially it's got a variable loading coil in the base.
I'm Scott, the screwdriver antenna, just a vertical antenna, what?
Yeah.
Okay.
The screwdriver portion, why they call it a screwdriver is that it's got a cordless screwdriver motor in the base that drives the whole thing up and down.
Okay.
And it's just about 2 o'clock. So let's just finish up this section and then we'll be in good shape for tomorrow, I think. So many good questions, you guys. So many good questions. What's the interaction between high standing wave ratio and transmission line loss? A bad match, and Merlin, this is for you. A bad match on your transmission line will waste power, period. The reason being that if I transmit power into this and I have a 5-to-1 SWR here, what happens is that my signal goes up, it hits this mismatch, and some of it goes out and some of it goes down. And that mismatch, you can look and see what the SWR is and figure out how much of it does that. It hits the tuner and goes back up. Some of it goes out and some of it comes back. It hits the tuner and some of it goes out and some of it comes back. Now,
all the more reason to use the auto tuner up at the antenna side.
That's exactly right.
Okay.
So, but now here's the other thing. Let's say that every time you pass through the cable, right? Because cable's not perfect, you lose some of your signal. So the worse the match that is happening, a bad match will be exacerbated by the lossiness of your cable. Like if you had lossless cable, all of your signal would eventually go out. Right? It would eventually go out. If you have very lossy cable, it'll get burned up as heat in the cable.
It's got tons of insulation on it. It's a huge, thick coax.
Yeah, well, I mean, but you know, it's really a question of if you start looking at it's because it's frequency dependent and it's going to be construction dependent. You have to look and see what it is and look at the curves in dB loss per 100 feet and also look at how long the cable run is.
Yeah.
So like if the way that mine works is I have a terrible mismatch and I know that, but I also have ladder line. I have 450 ohm window line, which has a loss of like 0.5 dB per 100 feet at HF, which is like nothing. So even if I have a really bad match here and the signal goes down and back and up and back and up and back a bunch of times, the loss is so low in that in the ladder line that most of the signal ends up going out anyway.
Okay. One more thing to be careful of. Yes.
Yeah. But that's why I use ladder line. And that's why a lot of people use ladder line. It's very forgiving compared to coax.
Right.
But you know, when it gets wet, it changes behavior a little bit. So it's a little tricky. Okay, let's see. The effect of transmission line loss on SWR. Well, transmission line loss will basically mean that a lot of your power doesn't make it back. The lossier the cable, the better your SWR will look. The reason that is true is if you think of it like this,
So let's say that this is a meter along with an SWR, along with a tuner, and you have a short circuit up here. You've shorted your cable by accident, right? And you've got 100 watts going out right here. And because of losses in your cable, you only have, let's say, 50 watts up at the cable. How much of that 50 watts is going to get bounced back from that short circuit?
50 watts.
50 watts. Okay. How much of that power, because of your cable, is actually going to make it back here?
It'd be half of it, wouldn't it?
It'd be half. So it's half of the 50. So now you have 100 watts going out and 25 watts coming back. You can go into the calculations and figure out what your SWR would be. If you had 100 watts going out and 100 watts going back, your SWR would be infinity. It would be as bad as you could get. But what if you've got 100 watts going out and only 25 watts coming back? That would be not so bad, right? It's still not great, but it's not so bad. But what do you actually have up there? You have a short circuit. And because of your lossy cable, you're being lied to. You're being told that your situation is not so bad.
Yeah.
Right.
Actually, it's bad.
When it actually is really bad. That's right.
Yeah.
Let's see. How does the attenuation of coaxial cable change as the frequency going up goes up? Your attenuation of your cable gets worse and worse and worse. It's just a function of the cable itself, of all cable. As frequency goes up, the attenuation gets worse. The main way of measuring attenuation is in dB per 100 feet, and it's frequency dependent. So it's dB per 100 feet at X frequency. And all the charts, all the graphs are going to display cable performance in that way. In addition to having like a maximum power carry. And finally, window line. Window line is twin lead that looks like this. That's typically going to be 450 ohms. Characteristic impedance. All right. And I think that's enough for today. Does everyone agree with that?
Yeah.
All right. Any questions?
Well, all this math has scared me to death of the test. I guess I'm going to be studying a lot.
No, what you got to do is just see, you've got the basic background now. Now you go and you start doing the practice tests like a little bit at a time, and you'll see that a lot of this stuff isn't scary at all, because you've now got the basic, you got the background behind it, and it's not alien anymore. I hope. When I do the technician class, I always couple an exam with it, and with this, I'm just like, this is not really something that I'm going to try to set up an exam for in the afternoon, because everyone's going to get ready when they feel like it. This is more kind of like a booster session,
Right.
Where we're going to go over all the material, but then you're going to ask lots of questions to try to understand the underlying stuff behind it.
It opens up more of the underlying stuff.
Well, right.
Like for me, some of the stuff that you did is explained a little bit more. Now I understand it a little bit better on some of the questions.
Well, that's good. That's the goal.
Yeah.
That's kind of what I hope, like, I mean, I can teach it all and say, go take your tests, but there's really no point to me doing that because everyone's doing it at their own pace.
Right.
It's really a case of, we're going to spend the amount of time necessary so that you understand the stuff that is eluding you.
Which is a lot of it. Hey, you said to be honest about it. Huh?
Yeah.
He gets my vote.
You got to start somewhere.
Yeah.
Thank you, Scott.
Thank you, Scott. We'll see you tomorrow.
All right. Have a good night.
All righty, sir. Bye-bye.
Thank you so much.
Peace, Scott.
Yeah, thanks,
Hey,
Scott.
hey, Ray,
Yeah.
is there anything else you want to cover?
We'll continue tomorrow and I'll go from there.
Okay.
Yeah, like I say, you fed me a lot right now to where my brain's, like I said, I'm kind of going.
Yeah.
But yeah, I'm going to do a lot more reading on it. My book, I think, is a little different too. That's the one I got. But the questions
Yeah, the page not, well, the questions are the same. but
pages
the
are different.
Yeah.
Yeah, pages are different. The page numbers. So yeah, yeah, I've been doing. I have taken a couple of practice tests, and I got 75%.
Good.
Yeah, but it still eludes me.
Yeah.
There's always one in there that throws you.
Well, keep going.
Yep. I
Nice
will.
thing
Thank
is
you,
there's no
sir.
time limit.
Yep. Thanks a lot.